Hello, where curiosity takes its shoes off and science pulls up a blanket. Tonight, we're going to drift into a question that's as strange as it is quietly thrilling. It's the kind of question that tiptoes into your thoughts when the lights are low and the world feels just a little too interconnected to be a coincidence. The question is this: could the Earth, not just the land or the air or the ecosystem, but the entire planet itself, be alive? Not in the way a bear is alive, or a tree, or even a coral reef, but in the way something immense and slow and silent might be. The kind of alive that doesn't breathe in lungs or speak in words, but still somehow knows. Before we get carried away, let's take a breath. Right now, wherever you are, you're sitting on or very near the surface of a planet. It's not just a rock floating through space. It's wet and windy and full of movement. It erupts and heals, freezes and thaws, decays and blooms. It makes weather. It supports life. In fact, it doesn't just support life. It creates the conditions for it. And it's been doing this for billions of years without ever seeming to need a manual. And here we are, you and I, very small parts of it, wondering if the whole thing might be more than the sum of its parts. Wondering if we'd been walking around on something that thinks in its own peculiar way, or feels, or dreams. That idea is not new. Long before satellites and sensors and seismographs, people talked about the Earth as if it were a someone, not a something. In myths and oral stories, mountains were bones, rivers were blood, forests were hair. The planet wasn't just a setting, it was a presence, a personality. In some stories, it was nurturing, in others, vengeful, but it was never just neutral, never just there. Now, you might say that was all metaphor. Humans explaining nature in human terms. Fair enough. But what if those metaphors weren't just colourful language? What if, in trying to give the Earth a face, people were picking up on something real, even if they didn't have the words or the science to prove it? Let's pause there for a moment, because it's easy to drift into fantasy when the question is this big. We're not talking about the Earth having eyes or whispering secrets through the wind, or waking up one day with a to-do list. What we're asking is more subtle. Is it possible that Earth operates as a whole system, not just mechanically, but meaningfully? And if so, does that qualify as some form of consciousness? We'll get into the definitions later. For now, let's just keep our minds slightly ajar. Look around your room. The furniture, the walls, the light from your phone or screen, all of it ultimately comes from the Earth. The wood, the metal, the electricity, the air you're breathing as you listen to this. Everything in your life has passed through Earth's hands, so to speak. It's easy to forget that, because has built so many layers between ourselves and the raw material of the planet. We live in apartments and cities, surrounded by plastics and networks and things we plug in, charge. But take away all of that, and we're still living inside the skin of a very old, very active, very complex system. And it's a system that doesn't sit still. Deep beneath your feet, even if you can't feel it, the ground is slowly shifting. Tectonic plates float on molten rock. Oceans rise and fall, not just with tides, but with long, slow pulses of temperature and salinity. The atmosphere breathes in carbon and breathes out storms. Clouds build, rain falls, rivers swell, aquifers refill. And somewhere on the other side of the world, a rainforest drinks deeply without asking permission. These aren't random events. They're part of cycles, massive, interconnected, self-balancing cycles that somehow keep going without anyone at the wheel. Or so it seems. In the 1970s, a scientist named James Lovelock proposed something that got a lot of raised eyebrows and a few nods of quiet recognition. He suggested that Earth behaves like a single self-regulating organism. He called it the Gaia Hypothesis, borrowing the name from the ancient Greek goddess of the Earth. The idea wasn't that the Earth is a goddess. It was that the systems of the Earth, climate, chemistry, geology, biology, aren't just operating in parallel. They're interacting in ways that seem purposeful. If the planet gets too hot, certain processes cool it down. Too much carbon, the oceans absorb it. Oxygen levels drop. Plants and microbes adjust. It's too much, as if the Earth notices when something goes out of balance and nudges it gently back into place. This was at the time a controversial suggestion, and to be fair, it still is. Many scientists accepted the idea of planetary feedback loops. Those are measurable, but the idea of Earth as a living being that was harder to stomach, partly because science, especially at that time, was deeply wary of anything that smelled like mysticism, but also because calling Earth alive forced a confrontation with a bigger, more unsettling thought. If Earth is alive, what does that make us? Are we its children, its cells, its thoughts, or something more like bacteria in its lungs? Those are not questions science is always comfortable answering, but they're the questions that keep coming back. 'Cause the more we study Earth, the harder it becomes to ignore just how integrated everything is. Coral reefs influence climate, volcanoes fertilize soil, animal migrations affect seed distribution, which affects forests, which affects rainfall, which affects rivers, and on and on. It's not just that everything's connected, it's that the connections seem to have memory, direction, sometimes even purpose. Think about this. If you take a single cell from your body, a liver cell, say, it's alive. It does its job. It reacts to stimuli. It metabolizes, but it doesn't think, not on its own. It's not conscious. You are, because you are the sum of all those cells, all communicating, all coordinated, all working together to keep the system going. Could it be that we, and whales, and fungi, and trees, and air currents, and ocean temperatures, are to Earth what those liver cells are to you? Individually meaningful, but only part of something larger. You don't have to answer that now. Just let the question sit. It's worth noting that when we talk about consciousness, we often default to a very narrow definition. Something human, something verbal, something that can name itself and say, I think. But even in the animal kingdom, consciousness comes in many shapes. An octopus solves puzzles with its tentacles. A raven remembers a human face for years. Elephants seem to mourn their dead. And there are levels below that, subtler forms of awareness. Plants respond to light and touch. Fungi change behavior in response to the environment. Microbes coordinate in colonies. Awareness isn't binary, it's a spectrum. And if awareness can exist without language, without eyes, without a nervous system like ours, then who's to say it couldn't exist in something as massive and slow as a planet? That doesn't mean Earth writes poetry or worries about taxes, but maybe it feels imbalance. Maybe it knows in some primitive way when something is off. Maybe it tries to correct, not because it wants to, but because it must. One of the strange things about living on Earth is how much it responds to us. We dig, and the land sinks. We pump gases into the air, and storms grow stronger. We remove forests, and droughts follow. In some cases, these are just the results of chemistry and physics. But in others, it almost feels like the Earth is reacting. Not lashing out, not punishing, just adjusting. Just changing shape in response to a presence that's getting a little too noisy. And that brings us to a quiet but persistent thought. If something reacts, is it aware, or at least aware enough? Consider a thermostat. It doesn't know it's keeping you comfortable, but it reacts to temperature changes in order to restore balance. Earth does this too, but on a vastly larger scale. It senses heat, stores water, releases gases, reflects sunlight. It's got systems on top of systems. The question is, are they just automatic responses, or is there something more like choice involved? We might not know, and maybe we're not supposed to. Maybe consciousness at planetary scale wouldn't feel like awareness at all. Maybe it would just look like stability. Maybe its thoughts are clouds. Maybe its feelings are feedback loops. Not personified, not poetic, just complex, persistent, and alive in ways we're not wired to recognize. Keep in mind, we didn't always think brains were where thought happened. Early philosophers believed consciousness lived in the heart or the gut. It took centuries of observation, dissection, and trial to map the seat of thought to the brain, and even now, we don't fully understand how thoughts form. So imagine trying to recognize thought in something the size of a planet. It's not just hard, it might be categorically different. Still, the clues are there. The coordination, the balance, the uncanny timing of events that unfold in response to change. And always the quiet sense that we're not alone. Not just because of animals or microbes or weather patterns, but because the whole system sometimes behaves as if it knows it's being watched. We'll get deeper into that soon. But for now, just notice what it feels like to sit with that possibility. Not to prove it or disprove it, just to consider that maybe, just maybe, the ground beneath you isn't just ground. Maybe it's part of something that thinks, something that notices, something that in some vast and unspeakable way might be listening. Here we are again, drifting a little deeper into the question we opened last time. And now that we have started wondering whether the Earth might be more than just background scenery, it's time to take a few slow steps backward. Not in our argument, but in our timeline, because long before anyone had the words for things like feedback loops or planetary law regulation, people had already started listening, not with instruments or algorithms, but with stories, rituals, and the quiet assumption that the land they walked on was in some way alive. This wasn't a fringe belief. In most early cultures, the idea that the Earth had a spirit or was a spirit wasn't even up for debate. It was a given, a foundation. The Earth gave food, shelter, seasons, storms. It gave birth and swallowed death. It moved slowly, but never aimlessly. And for people who depended on its rhythms for survival, those patterns felt a lot like personality. Consider how often the ground appears in early belief systems, not just as a place, but as a presence. Many indigenous cultures describe Earth as a mother, not metaphorically, but relationally. The Hopi people of the American Southwest see the Earth as a living being, the origin of all life, to be honored and cared for. In Maui traditions, Papa Tuanuku is the Earth Mother, lying beneath Ranginui, the Sky Father, their children separating them to make space for light. In Andean cosmology, Pachamama is the goddess of the earth, both nurturing and fierce, a being with whom you can be in or out of balance. These are not just poetic names for soil and stone. They're roles, identities, and they come with responsibilities, not just for the land, but to the land. Even the word earth in many languages carries a dual meaning, both the ground beneath your feet and the larger whole that holds you. It's never just dirt. It's something older, deeper, and somehow aware. And while these beliefs took different forms around the world, the common thread is hard to ignore. Humans didn't see themselves as separate from the earth. They saw themselves as part of it, bound by mutual relationship. Now, you might say that's just mythology. And yes, from a modern perspective, these stories don't operate on scientific proof. But that doesn't mean they aren't grounded in observation. Early peoples were incredibly attuned to the world around them. They knew the migration of animals, the blooming cycles of plants, the warning signs of storms. They watched the horizon like a heartbeat and read the stars like a clock. If they spoke of the earth as living, it wasn't out of ignorance, it was out of attention. And attention is often where science begins. Think of it this way. Long before we had microscopes, people suspected that sickness could pass from one person to another. They didn't know about bacteria or viruses, but they noticed patterns, and so they made stories to explain those patterns. Later, science caught up and gave those stories new names. What we now call germs used to be called spirits. What we call systems were once called gods. So when we hear that early cultures treated mountains as sacred, or sang to rivers or thanked the soil after harvest, it's worth asking, what did they notice that we no longer do? What signals, what changes, what rhythms felt so consistent that they began to seem intentional? In Australia, Aboriginal songlines map the landscape, not just physically, but spiritually. The songs aren't just directions, they're living records of how the land behaves, where water hides, when plants bloom. Each verse encodes generations of knowledge about a land that was never seen as inert. To walk the land was to walk inside a story, and to sing it was to keep it alive. In Japan, the concept of kami includes spirits that reside in natural features, rocks, trees, rivers. These aren't separate from nature. They're nature seen with a different kind of lens, and they're treated with respect because they are believed to respond not symbolically, but actually again and again, across continents and eras we find the same pattern. Earth is not just used, it's related to, listened to, interacted with. And while modern science may not accept the literal truth of Earth as a spirit, it is slowly rediscovering the complexity behind what those old stories might have been pointing at. For example, we now know that forests are not just collections of trees. They're connected underground by vast fungal networks that transmit nutrients, warnings, and chemical messages. When one tree is under attack by pests, it can signal nearby trees to prepare. When young saplings grow in the shade, older trees can feed them through their roots. This system has been called the wood wide web, but to someone thousands of years ago, watching plants seem to cooperate. It might have just looked like the forest was thinking. And perhaps, in a way, it was. The same goes for weather. If you live close to the land, you notice things. The shift in wind before a storm, the way birds fall silent before heat waves, the return of certain smells when rain is near. Over time, those patterns become part of your worldview. They're not random. They're signs. And when signs speak, someone must be speaking through them. This isn't about superstition. It's about how observation becomes narrative when science hasn't yet drawn the lines. And sometimes those narratives end up pointing to truths science only later confirms. When we look at ancient agricultural practices, we see the same layered relationship. Traditional farmers in many parts of the world use methods that maintain soil health not through external inputs, but through rotation, rest, and intuition. They don't see soil as a blank slate. They see it as alive with needs and limits. And those methods often lead to more sustainable yields than industrial approaches, not because they're less advanced, but because they're more in tune. Even rituals that might seem symbolic often had practical outcomes. Burning sage to purify a space has been shown to reduce airborne bacteria. Offerings left for river gods may have once acted as early water monitoring systems. When the water changed color or smell, it was noted not just as contamination, but as a change in mood. The earth was treated like a being because it behaved like one, and if that seems unscientific, it might be worth asking, how do we define a being? We often think of a life as something that moves, breathes, consumes, and that makes sense at a human scale. But if you stretch the timeline, mountains move too. Rivers carve paths, continents collide. The earth does breathe in its own slow, massive way, through carbon cycles, through weather systems, through the rise and fall of ecosystems. It just happens so gradually that we only notice in retrospect. The idea that Earth is alive isn't just cultural nostalgia, it's a framework that may have helped early society survive. When you see the land as sentient, you don't take without thinking. You don't dump waste into rivers that can hear you. You don't strip forests that are watching. You live with caution, gratitude, sometimes fear, but always relationship. And here's where it starts to get more interesting, because now, as we face global environmental changes, modern science is beginning to echo some of those older intuitions. We use phrases like Earth system science and planetary boundaries to describe the interconnectedness of climate, water, soil, biodiversity. We talk about resilience, balance, thresholds. And the more we study, the more we realize these systems aren't linear. They respond sometimes slowly, sometimes suddenly. They act like systems that want to maintain homeostasis, like systems that notice, not in a mystical way, not in a divine way, but in a way that blurs the line between mechanical and meaningful. In recent years, researchers have started applying network theory to ecosystems, finding that certain species act like nodes, critical connectors in the flow of energy and information. When those nodes are removed, the system struggles. It's not a chain, it's a web, and webs are known for their sensitivity. A touch at one end sends ripples to the other. Even something as simple as a population change in one insect can ripple out into climate, crop yield, water availability, and those ripples loop back. They don't just go out, they come in. The Earth, in other words, isn't just a platform for life, it's a participant in it. It's not just what we live on, it's what we live through. And maybe in some slow and system-wide way, it's what lives through us. As we move forward, we'll look more closely at what science has to say about this. Not in the language of myth, but in the language of data, systems, biology, feedback, adaptation. We'll ask how life emerged, how it persists, and what it might mean when life and environment become indistinguishable. But for now, just remember this. Long before we had charts or climate models or atmospheric simulations, we had stories. And those stories said the Earth is not just where you live, it is something you are part of. It listens, it changes, it remembers. Not because people were primitive, but because they were paying attention. Now that we've spent time with the older ways of seeing Earth, ways that treated the planet not as scenery, but as a living presence, we find ourselves at a curious turning point. For centuries, the modern scientific worldview moved away from that kind of thinking. The Earth, once considered a parent or a spirit, was gradually reimagined as an object, a machine, a set of measurable parts. But not everyone was satisfied with that view. And in the late 20th century, an idea emerged that quietly echoed those ancient beliefs. Only this time, it came dressed in data, models, and systems theory. It was called the Gaia Hypothesis. The name alone raised eyebrows. Gaia, from Greek mythology, the personification of Earth, a name that sounded more poetic than scientific. And yet, the idea behind it was rooted in very real questions about how the planet works, and whether all its parts, air, water, land, life, might be more than just pieces of a puzzle. Might they together function like a single organism? The hypothesis was first proposed in the 1970s by James Lovelock, an atmospheric chemist, and was later expanded in collaboration with microbiologist Lynn Margulis. They were trying to answer a simple but deeply unsettling question: why has Earth's climate remained so stable for so long? After all, when you look at neighboring planets like Mars or Venus, you see extreme conditions. Venus is a furnace, Mars is a frozen desert, but Earth is oddly consistent. Not static, not unchanging, but reliably habitable. For over 3 billion years, despite massive changes in the sun's output, asteroid impacts, and volcanic eruptions, Earth has stayed within the narrow window of conditions that allow life to exist. That doesn't seem like an accident, and so Lovelock asked, could it be that life on Earth doesn't just adapt to the environment, but actively helps maintain it? The idea wasn't that the Earth was conscious in any human sense. It was that the entire biosphere, the sum of all living organisms, interacts with the physical environment in ways that regulate temperature, atmospheric composition, ocean salinity, and other factors. In other words, life helps create and preserve the conditions for life. This was a radical suggestion. Until then, the mainstream view in biology was that life evolved to fit the environment, not the other way around. But Lovelock's theory suggested a loop. Life shapes the environment, and the environment shapes life, and together they form a self-regulating system. To make the idea more tangible, he used a metaphor, a fictional model called Daisy World. Imagine a planet like Earth, but covered only in black and white daisies. The black ones absorb heat, the white ones reflect it. As the planet warms, white daisies spread, cooling the surface. As it cools, black daisies take over, warming it up. Without anyone planning it, the balance of daisies keeps the planet's temperature stable. It's a feedback loop, simple but effective. In the real world, things are more complicated, of course, but Lovelock pointed to real-life feedback loops that seem to support his hypothesis. For example, marine algae release compounds that help form clouds, which reflect sunlight and cool the earth. Rainforests transpire water vapor, creating rain systems that help sustain the forest itself. When trees grow, they draw down carbon dioxide, altering the atmosphere. And on a longer timescale, the weathering of rocks draws carbon from the air into the ground, a process influenced by microbial life. These are not isolated effects. They're worked, interlinked, and together they seem to create a kind of planetary homeostasis, a tendency toward balance. At first, the Gaia hypothesis was met with skepticism. Some scientists found it too vague. Others were uncomfortable with its spiritual overtones, even if unintentional. And to be fair, early versions of the idea were more suggestive than rigorous. But over time, as more data emerged and Earth system science developed, many of its core ideas gained traction. What changed wasn't so much the evidence, though there was more of it, but the framing. Scientists began using different language. Instead of saying the Earth behaves like a living organism, they talked about coupled systems, feedback dynamics, resilience, and nonlinear interactions. The concept of Gaia was softened into a model of planetary regulation, but at its heart, the question remained the same. Is the biosphere just a collection of parts, or is it a unified system that maintains itself? Today, many aspects of the Gaia hypothesis are considered foundational in Earth system science. It's accepted that life influences climate, and vice versa. What's still debated is how far that influence goes, and whether it implies coordination, or just coincidence. Some argue that what looks like regulation is just the result of evolution. Species that benefit from stabilizing their environment survive longer. Their actions accumulate, creating the appearance of balance. No intent, no awareness, just selection. Others aren't so sure because the feedback loops we see aren't always local. They span continents, not oceans, and they involve organisms that aren't aware of each other. How does something that complex emerge from individual behavior? This is where the idea of emergence comes in. Emergence is what happens when simple parts create complex outcomes. An ant is not intelligent. A colony behaves as if it is. A neuron doesn't think, a brain does. Maybe life on Earth works the same way. Maybe no organism is trying to stabilize the planet, but their combined actions produce that effect. Not because they plan it, but because they're part of a larger pattern. And maybe, just maybe, that pattern is a kind of awareness, not of thoughts or language, but of maintenance, persistence, continuation. If you think of a body, it has systems to keep itself alive. Immune responses, temperature regulation, nutrient flow. These systems don't need to know they're part of a body to do their job. They just do it. And the result is health, stability, awareness that something is wrong, even if that awareness doesn't come with words. So, what would that look like at planetary scale? Maybe a rainforest that knows when to seed itself. Maybe coral reefs that grow where ocean currents shift. Maybe the Earth doesn't have a brain, but maybe it doesn't need one. Maybe the network is enough. This brings us to a tension in how we think about consciousness. We tend to associate it with centralization, with a mind, a control center, a singular perspective. But in nature, that's not always how things work. Slime molds solve mazes without neurons. Flocks of birds change direction without a leader. Even the human brain is less of a command post and more of a conversation between competing systems. So if consciousness can be distributed, decentralized, emergent, why not at the level of a planet? This isn't to say Earth has intentions, but maybe it has tendencies. Maybe it leans toward life because life is what keeps it stable. Maybe it adjusts when systems go too far. Maybe what we've called nature's balance is something closer to nature's instinct. And if that's true, then the Gaia hypothesis isn't just an elegant idea. It's a quiet return. Not a return to myth, but a return to relationship. To the sense that Earth isn't just where life happens, but how life happens. That living things don't just survive within boundaries. They help draw those boundaries. Of course, like any complex system, Earth can be pushed beyond its limits. Feedback loops can fail. Thresholds can be crossed, and when they are, the system doesn't fight back. It changes. The balance shifts. The conditions become less friendly to life. Not out of malice, just out of math. This is where the Gaia idea becomes more than a thought experiment. It becomes a warning. Because if the planet is a system that tends toward balance, and that balance is maintained by life, then what happens when life begins disrupting that system faster than it can adapt? Climate change is often described in terms of parts per million degrees of sea rise, but it can also be understood as the Earth's regulatory system straining to respond. Warmer oceans absorb less carbon, melting ice reflects less sunlight, drying forests lose their role in rainfall patterns. The loops are still there, but they're spinning the wrong way. And unlike the slow changes of the past, these are happening rapidly. Geologically speaking, we've hit fast forward, and the planet is adjusting. Not to save itself, but to rebalance. The question is, will that new balance still include us? Gaia, if we can still use that word, is not sentimental. It doesn't prefer any one species. It doesn't reward intelligence or technology. It rewards integration, the ability to participate in the system without breaking it. And that may be the most unsettling part of all. Because if Earth does operate like an organism, then it may also have a kind of immune system. Not literal white blood cells, but responses to imbalance. Heat waves, droughts, floods, and fires may not be punishments. They may be symptoms, not of anger, but of regulation. And in that sense, humanity might need to rethink its role, not as master or steward, but as part of a body, capable of harming it, capable of healing it, but never separate from it. So the Gaia hypothesis, whether taken literally or not, invites a shift in perception, away from ownership and toward belonging, away from control and toward participation. Because whether Earth is conscious or not, it is responsive, it adjusts, it adapts, and it continues. And so perhaps should we. The idea of Earth as a self-regulating system brings us to something even more tangible. If you sit quietly, really quietly, you might notice something strange about the world around you, not in a supernatural way, not in visions or whispers, but in rhythms. Slow, deep, often invisible rhythms. They're happening all the time. And some scientists, researchers, and curious observers have begun to wonder, do those rhythms amount to something more than coincidence? Could they be signs of something like a planetary pulse? The word pulse is loaded. We associate it with life. Something living has a beat. Hearts, yes, but also breath, tights, sleep, hunger. Pulses imply regulation, a kind of internal timing. They're patterns that tell us something is active, responding, maintaining itself. So, if Earth has rhythms, real measurable ones, what are they doing? What are they keeping track of? Start with the basics. We already know the planet turns. One full rotation every 24 hours, give or take a few milliseconds. It's regular, dependable, ancient, but it's not just movement. It's a cycle that governs everything, from photosynthesis to animal behavior to the chemical clocks inside our own cells. Circadian rhythms, as they're called, don't just belong to people. They show up in birds, insects, bacteria, even fungi. Everything that lives on Earth has, in some way, synced itself to the turning of the planet. And then there's the orbit. One full journey around the sun every 365. 25 days. Another deep rhythm. It shapes seasons, migrations, reproduction, weather systems. Trees bud, flowers bloom, animals move. These aren't random reactions, they're tuned responses. Earth's position in space sends cues through light, heat, and gravity, and life listens. Those cycles are easy to see. We've built calendars around them, but they're not the only ones. The oceans have their own timing. Tides rise and fall, not just daily, but on longer, more subtle cycles tied to the moon's orbit and the sun's position. There's the fortnightly spring and neap tides, the monthly lunar cycle, and even 6 nodal cycles that influence weather and wave patterns. Coastal ecosystems respond to these shifts. Fish spawn at certain phases. Crabs move with the moon. Corals, oddly precise, release their eggs all at once, as if keeping time with some underwater clock. Beneath the surface, there's more. Ocean currents move heat across the globe in vast looping highways. The Atlantic marginal overturning circulation, for instance, brings warm water from the tropics northward and cold water southward, in a conveyor belt that affects weather onto multiple continents. This system pulses too, slowing, speeding, adjusting based on salinity, temperature, and wind. It doesn't just respond to climate, it helps shape it. Deep in the Pacific, there's the El Niño Southern Oscillation, a pattern of warming and cooling ocean temperatures that shifts global rainfall, droughts, and storms. It follows a loose rhythm every 2 to 7 years. Not clockwork, but not chaos either. Something in the ocean remembers, something resets, and Earth's atmosphere joins the chorus. Pressure systems rise and fall in patterns. The Madden-Julian Oscillation brings rain across the tropics every 30 to 60 days. The Quasi-Biennial Oscillation flips winds in the stratosphere every 28 months. Polar vortexes pulse with the seasons, swelling and shrinking like lungs under strain. None of this is random, none of it is simple, but all of it repeats. So what do we make of this? Dozens, maybe hundreds of overlapping cycles, each with its own beat, too slow to hear, too large to feel, but together they shape the world we live in. And if that's not a pulse, then what is it? Of course, some might say that calling these rhythms a pulse is just metaphor again, that we're projecting our own biology onto a system that's simply running on physics. And there's truth to that. Tides rise because of gravity. Seasons happen because of axial tilt. No heartbeat required. But here's the thing. Those explanations don't make the rhythms less real. They make them more interesting. Because they show us that Earth isn't just reacting to external forces, it's integrating them. Consider the Schumann resonance. It's a set of electromagnetic waves that circle the globe, trapped between the Earth's surface and the ionosphere. They're created by lightning and bounce around the planet, forming standing waves. The lowest of these frequencies, around 7.83 Hz, has been nicknamed Earth's heartbeat by some. That's not a scientific term, but the comparison lingers, not just because it's rhythmic, but because it's persistent, global, and in some strange way, calming. There are researchers studying correlations between these frequencies and human brain waves. The results are preliminary, and the mechanisms are unclear, but the curiosity is there. Are we picking up signals from the planet? Are we more synchronized with our environment than we realize? It's not just electromagnetic fields. Even seismic activity follows patterns. Earthquakes are often seen as unpredictable, and in many ways they are. But tectonic plates don't move randomly. They slide, collide, and subduct in cycles that build up tension over decades or centuries. Volcanoes pulse too, not in seconds or minutes, but in long, patient exhalations. Mount Etna has erupted on and off for thousands of years, like a breath drawn too deep. Yellowstone breathes with the rise and fall of its caldera. Not myth, not metaphor, measurement. The Earth swells and relaxes as gravitational forces from the moon and sun stretch its crust, ever so slightly. These earth tides are tiny, just a few centimeters in most places, but they're consistent. They affect groundwater levels, magma pressure, even the frequency of small tremors. In a way, the planet moves like a chest breathing in sleep, subtle, slow, but never still. And then there's carbon. The carbon cycle doesn't just describe how carbon moves through the air, land, ocean, and living things. It also has a rhythm. Plants absorb carbon during the growing season, releasing less into the atmosphere. In fall and winter, decay returns carbon to the air. Satellites can track this pulse. More absorption in the northern summer, more release in the northern winter. A planetary exhale, then inhale, back and forth, steady, vital. Some scientists have even proposed looking at Earth's biosphere as a kind of metabolic system. It consumes energy from the sun, processes it through photosynthesis, distributes it through food webs, and releases waste in the form of heat and decomposition. It adjusts when inputs change. It slows down in winter. It accelerates in spring. If that doesn't sound like metabolism, it certainly looks like it. What does all this mean? Well, maybe nothing on its own. Cycles don't equal consciousness. Pulses don't prove purpose. But what they do suggest is something we often overlook. Earth is not still. It's not static. It's not passive. It's active, layered, and incredibly responsive. And when systems are that responsive, when they react, adapt, and return to balance, it's natural to ask whether they're also in some sense aware. Not aware like we are, not with thoughts or feelings or language, but aware in the way a well-tuned body is aware of imbalance. Not by thinking about it, but by responding to it. If your temperature rises, you sweat. If you're hungry, your body signals you. If you're hurt, cells swarm to repair. None of that requires conscious thought. And yet, it's all meaningful. It keeps you alive. So maybe the planet does something similar, not with intentions, but with processes. Not with awareness, but with action. Of course, there's a risk in taking this too far. Earth is not a person. It doesn't want, or wish, or decide. But that doesn't mean it's just a backdrop either. These rhythms, these cycles, these pulses, they suggest something more than chaos, something more than randomness. They suggest that Earth behaves like a system that wants to persist, and systems that want to persist adjust. We see that now in the face of climate change. The planet is changing. The rhythms are shifting. The pulses are speeding up in some places, slowing down in others. Forests are absorbing less carbon. Permafrost is releasing more. Oceans are growing warmer, which weakens their ability to store heat. Ice melts faster. Storms form more quickly. The loops are still there, but the beat is getting irregular, and that's worth paying attention to. Not because Earth is angry, or vengeful, or conscious in a way we can measure, but because a stable planet, one with a steady pulse, is what life depends on. Maybe the real insight here isn't whether Earth is alive, but whether we've been listening. The signs are there, the rhythms are there. They're subtle, quiet, slow, but they're real. And maybe if we tune in, if we learn to feel the beat beneath our feet, we might begin to understand not just the Earth's rhythms, but our place within them. The deeper you go into the rhythms of the planet, the more difficult it becomes to separate life from the systems that support it. Air, water, soil, none of them are truly lifeless. They interact with biology in ways that go far beyond just enabling it. They're shaped by it, sustained by it, even transformed by it. And nowhere is this more obvious than in the forests and the oceans. These aren't just environments where life happens. They're engines of change. They take in, release, adjust, and cycle. In many ways, they are the breathing and beating centers of Earth itself. When people talk about forests as the lungs of the planet, they're usually referring to the fact that trees and plants absorb carbon dioxide and release oxygen through photosynthesis. That's true, of course, but it's only a small piece of what's really happening. Forests don't just produce oxygen, they influence weather, they regulate temperature, they affect rainfall patterns thousands of kilometers away. There are vast network systems that shape the chemistry and physics of the atmosphere, not just locally, but globally. Consider the Amazon rainforest. It's often described as a carbon sink, a place where carbon dioxide is absorbed and stored, helping to regulate the climate. But that's not the full story. The Amazon also generates its own rain. Trees there release water vapor through transpiration, contributing moisture to the air. This moisture forms clouds which produce rain, which feeds the trees. It's a self-reinforcing loop, a kind of biological feedback system. And it doesn't just affect the Amazon basin. The water vapor from those forests drifts on air currents and influences weather across South America. Even rainfall patterns as far away as the United States and Africa can be affected by the health of the Amazon. This pattern isn't unique. Forests across the globe play similar roles. In temperate zones, boreal forests help cool the planet by storing carbon in their soils and influencing albedo, the amount of sunlight reflected by the Earth's surface. In tropical regions, dense canopies maintain humidity, stabilize soil, and cycle nutrients with astonishing efficiency. These forests don't just live within the climate, they co-create it. And then there's the way forests communicate. This isn't science fiction. We now know that trees are connected through underground fungal networks that allow them to share resources and even send signals. When one tree is under attack from pests, it can release chemical signals that prompt nearby trees to boost their defenses. Older trees, sometimes called mother trees, can distribute nutrients to younger ones. These aren't metaphors, they're observable phenomena. Forests in a very real sense have memory, response, and structure. If forests are Earth's breath, then the oceans are its circulation, covering over 70% of the planet's surface. Oceans absorb heat, carbon, and oxygen, redistribute them, and send them back into the atmosphere in new forms. They store more carbon than the atmosphere and the land combined. They move vast amounts of energy from the equator toward the poles. They influence the formation of clouds, the paths of storms, the success of harvests. And like the forests, they don't operate randomly. They operate in cycles. Take the biological pump. This is the process by which the ocean pulls carbon dioxide from the atmosphere, converts it into organic matter through photosynthesis, in microscopic plankton, and sends it down into the deep sea. When those organisms die, this carbon can remain buried for centuries. Without this pump, atmospheric carbon levels would be far higher, climate would be different, life on land might be far more precarious. Plankton, so small we can't see them with the naked eye, perform nearly half of all photosynthesis on Earth. They feed fish, support whales, and shape the chemical composition of the air. And yet they rely on the movement of ocean currents, temperature gradients, and nutrient upwelling to survive. They're fragile, and when ocean conditions change, they respond quickly. Then there's the thermomaline circulation. This is the great conveyor belt of the oceans. Driven by differences in temperature and salinity, it moves water across entire basins, bringing warm water from the tropics to northern latitudes, and returning cold water to the deep. This circulation keeps regions like Western Europe much warmer than their latitude would suggest, and it's part of a larger planetary scale system that helps stabilize global climate. But it too can shift, and when it does, it brings changes that echo through ecosystems, weather systems, and agriculture. Some paleoclimate records suggest that major disruptions in this circulation have coincided with rapid climate events in Earth's past. And today, as ice melts and salinity changes, there are signs that parts of this conveyor belt may be weakening, not because of any intention, but because the system is adjusting to new inputs. The oceans also produce aerosol particles, tiny droplets that enter the atmosphere and help form clouds. They reflect sunlight, affect rainfall, and shape the planet's energy balance. These aerosols don't come from factories or pollution. They come from plankton, fish, sea spray. They're part of a vast invisible exchange between sea and sky. And that exchange isn't just chemistry. It's chemistry shaped by life. Even sound moves differently in the ocean. Whales and dolphins navigate with echolocation. their songs bouncing off the walls of underwater canyons. Coral reefs pulse with clicking shrimp and burbling fish. Storms rumble through the water like distant drums. And deep below, tectonic activity sends slow waves rippling through the crust. It's not just the ocean moving, it's the ocean speaking, not in language, but in signals. The more we study these systems, the more we find that they don't just support life, they behave like life. They change in response to stimuli, they stabilize themselves after disruptions, they maintain internal conditions within certain limits. That's the basic definition of homeostasis. And homeostasis is one of the things we associate with living systems. None of this means the oceans or forests are conscious, but it does mean they're active, dynamic, essential, and they respond to change. Not all systems do, but living ones almost always do. That responsiveness raises questions, because now, in the face of global environmental stress, we're seeing those systems start to shift. The Amazon, once a carbon sink, is now emitting more carbon in some regions than it absorbs, due to deforestation and warming. Coral reefs are bleaching and dying as ocean temperatures rise, reducing biodiversity and weakening the biological pump. Phytoplankton populations are shifting, changing the base of the food web. The great conveyor below and the feedbacks are compounding. These changes aren't just statistics, they're symptoms, signs that something is no longer holding steady. But here's the part that's easy to miss. When forests and oceans start to shift, the planet doesn't just fall apart, it reorganizes. It tries to find a new balance. Species adapt, currents realign, new patterns form, ecosystems migrate, split reform. It's not always a graceful process. There's loss, extinction, breakdown, but there's also reconfiguration. The system doesn't collapse immediately, it adjusts. The question is, can it adjust fast enough? Because in the past, these shifts happened over centuries, sometimes millennia. Now, we're pushing those systems at speeds they weren't designed to handle. And when feedback loops break, the system doesn't just bounce back. It can jump to a new state, one with very different conditions, hotter, more chaotic, less predictable, still functional perhaps, but not necessarily habitable in the way we've known. That's the real risk. Not that Earth will die, but that it will change, that the breath will become erratic, that the heartbeat will falter, and that the conditions we depend on will give way to something new. Not because the planet fails, but because it continues. We don't often think about that. We assume the systems around us are stable, because they've always been here. But the breath of forests and the heartbeat of oceans aren't permanent. They're maintained, not by design, but by balance. And balance can be lost. That doesn't mean we're helpless. In fact, understanding these systems, how they work, how they respond, gives us a kind of agency. We can stop interrupting their rhythms. We can learn to support their cycles, instead of overwhelming them. We can act not as outsiders, but as participants, cells within the system. Because if Earth is alive in any meaningful way, then we are part of its life. Not special, not separate, but included. And that changes the question. Not is the Earth alive, but how do we live well within something that already is? It makes sense now to shift our attention downward, past the canopy and weather, past the sounds and signals of ocean and sky into the dirt. Not in the dismissive sense, but in the literal one. Because if you're wondering how a planet might perceive itself, how it might coordinate all its parts without a brain, without a control center, then you eventually end up here in the soil, or more precisely, in what lives inside it. It's easy to overlook the ground. For most of us, it's just something we walk on, build on, farm on, dig through. We see it as a background, useful, sure, fertile, hopefully, but mostly inert. A place where things grow, not a thing that grows. But that's an illusion, one built on the scale we're used to. Soil isn't just matter, it's process. And for the last few decades, researchers have been uncovering something that changes the way we think about ecosystems, about communication, even about intelligence. They found something like a network, a slow, quiet, invisible network of signals and responses, and coordination, not just between individual organisms, but between entire species, and not just species, but entire ecosystems. It's called the mycorrhizal network, and in some ways it behaves like a nervous system. The term comes from the Greek words for fungus myko and root rhiza, Mycorrhizal fungi are microscopic filaments that grow in and around the roots of plants. They form symbiotic relationships, mutually beneficial partnerships. The plant provides sugars produced through photosynthesis. The fungi, in return, help the plant absorb water and nutrients from the soil. That's the basic exchange. It's been going on for over 400 million years. But what makes this more than a neat example of cooperation is what happens at scale. These fungi don't just connect to one plant. They connect to many, dozens, hundreds. Entire forests can be interlinked by a single fungal network, forming a kind of underground web. Through it, trees can exchange carbon, nitrogen, phosphorus. They can send signals, even alerts. Some studies have shown that when one tree is attacked by pests, it can send chemical warnings through the network, prompting neighboring trees to activate their own defenses. Others have found that older trees, sometimes called mother trees, share nutrients with younger saplings, especially those in shade or distress. The network doesn't just pass resources, it seems to direct them. This raises questions. How are these decisions made? How does the system determine where resources go? Is there a kind of memory involved? Coordination. The fungi themselves don't have brains. Trees don't have nerves. But somehow the system behaves like a distributed intelligence. Suzanne Simmer, a forest ecologist who helped pioneer this research, has described it as a communication network. She and her colleagues have mapped these connections, showing how signals can travel from one part of a forest to another, not instantly, but reliably. And the signals aren't random. They change based on context. They carry information. What does that sound like if not a nervous system? In animals, nerves transmit electrical signals. They carry pain, pleasure, awareness of balance, changes in temperature. But the key function isn't speed, it's coordination. The nervous system helps different parts of a body stay in sync, to respond to the environment, to maintain balance. The soil, it turns out, does something similar. It receives inputs, moisture, temperature, roots, microbes, chemicals. It processes them, it redistributes them. It responds, and it does all this without a central command. It's not a brain, but it behaves like a brain-like thing, decentralized, persistent, always adjusting, and it goes beyond trees. The soil is home to a vast number of microbial organisms, bacteria, fungi, archaea, nematodes. A single teaspoon can hold billions of individual organisms, representing thousands of species. They form networks too. Some cooperate, others compete. They produce chemicals that affect plant growth, disease resistance, even mood in animals. Some scientists are beginning to refer to the soil microbiome, the way we talk about the gut, microbiome in humans, as a critical system that influences everything from health to behavior. And like the gut, the soil can be disrupted. Agricultural chemicals, compaction, erosion, these don't just remove nutrients, they break networks, they reduce complexity. And when complexity drops, so does resilience. The system becomes less responsive, less adaptive, more fragile. This matters because healthy soil isn't just about farming. It's about carbon storage, water filtration, and the cycling of nutrients that support all terrestrial life. When soil functions well, ecosystems stay stable. When it doesn't, the effects ripple outward into forests, into rivers, into the atmosphere. Some researchers have begun exploring whether these underground networks respond to external stress in ways that go beyond individual organisms. For example, if a forest experiences drought, can the fungal network help redistribute water to where it's needed most? Does the system store information about past conditions? Does it learn what responses work best? These are open questions. The answers depend on how we define intelligence, memory, response. But the patterns are there, and they resemble systems we usually associate with awareness. Think about what that implies. Beneath our feet, there may be something like a planetary web, not just rooted in place, but sprawling, connecting species, transporting signals, redistributing energy. It doesn't think exactly, but it adapts. It balances. It responds to injury. It recovers. This raises another thought. If forests and fungi and soil microbes are all connected, if they form something like a single system, then what happens when we interfere with that system, without realizing what we're touching? Deforestation, for instance, doesn't just remove trees. It removes nodes in the network. It breaks connections. In some areas, this has led to declines in soil fertility, water retention, biodiversity, not just because of the loss of vegetation, but because of the loss of structure. The underlying meshwork that made the ecosystem function is gone, and rebuilding it isn't as simple as planting new trees. The network needs time, cooperation, memory. So maybe the Earth doesn't need a nervous system like ours. Maybe it already has one. Not fast, not centralized, but deep, ancient, and everywhere. When we walk through a forest, we don't see this network. We see trunks, branches, leaves. But underneath, in the dark, the slow, the damp, there's movement. Not in meters, but in adaptations per year. Signals pass, responses happen, feedbacks adjust. And this isn't metaphor. It's measurement. It's lab work, field work, peer-reviewed studies. It's data that points to a reality we're only beginning to appreciate. That the planet's ability to maintain itself doesn't rest in any single organ. It rests in systems that span the whole. And when you think of it that way, the question of whether Earth is alive begins to look less speculative, not because it acts like a person, but because it acts like a living system, one with circulation, metabolism, feedback, repair, and maybe even something like sensation. It's only natural to lift our gaze again, to look up into the air, the clouds, the atmosphere, the part of Earth that's always in motion. This is the layer we breathe, where weather is born, where the edges of temperature and pressure rub against each other and shape what we experience as climate. And among the most dramatic expressions of that system are storms. We usually think of storms as events, things that happen. A hurricane approaches, a thunderstorm builds, a tornado forms. We talk about them the way we talk about accidents or intrusions. But storms aren't just outbursts. They're the result of complex interactions, and in some cases, their behavior is so intricate, so finely tuned conditions, that it raises an unusual thought. Do storms behave like systems that want something, not in a conscious way, not in the way an animal might want food or shelter, but in a functional sense? Because when you watch how storms form, how they gather strength, how they draw from multiple sources and then shut themselves down when those sources are gone, it can start to look like more than just reaction. It can start to look like strategy. Take hurricanes, also called tropical cyclones, depending on the region. They require very specific conditions to form. Warm ocean water, usually above 26.5 degrees Celsius, a pre-existing weather disturbance, moist air, low vertical wind shear. If any of these are missing, the storm doesn't happen. But when the ingredients are there, the system begins to build itself. Air rises from the warm surface of the ocean, carrying moisture upward. As the air cools, the moisture condenses, releasing heat. That heat fuels more rising air, which pulls in more air from below, which creates wind. And as the Earth spins, the Coriolis effect gives the system its spiral. It's not a single gust or a one-time lift. It's a self-sustaining loop. Heat feeds motion. Motion pulls in fuel. Fuel builds strength. The storm organizes itself. This process can last for days. The storm doesn't just form and go. It adjusts to its environment. If wind shear increases, it weakens. If it passes over cooler water, it slows. If it hits land, its source of energy is cut off, and the structure collapses. It's not alive, but it behaves as if it recognizes conditions, as if it knows how to persist. Some researchers have described hurricanes as heat engines. They move energy from the warm ocean to the upper atmosphere, redistributing heat. In that sense, they serve a planetary function. They don't just cause destruction, they also regulate, but they do it through turbulence. And turbulence, it turns out, can be very precise. Studies have shown that the eye of a hurricane, a near-calm center surrounded by chaos, is incredibly well structured. The winds circulate in tight bands, the temperature gradients are sharp, and the symmetry at times is astonishing. It's a system that's constantly correcting itself, responding to imbalances, maintaining coherence even as it barrels forward. That ability to self-correct, to stabilize around a core, is something we usually associate with intelligent systems. And while storms don't think, they do refine themselves. The same is true on a different scale with thunderstorms. They form when warm, moist air rises rapidly, often along a front where two air masses meet. The rising air cools, condenses, releases energy, and drives further upward motion. This creates cumulonimbus clouds, tall, towering structures that can reach the stratosphere. Inside these clouds, something strange happens. Water droplets, ice crystals, and air currents collide in just the right way to separate electrical charges. The top of the cloud becomes positively charged, the bottom negatively charged. And when the difference becomes large enough, the charge is released as lightning. But the system doesn't just discharge once. It builds, resets, and fires again. There's a rhythm to it. Pulses of energy, moments of tension, releases, and it all happens within the bounds of a system that's not static. It grows, moves, adapts. Some storms become supercells, rotating thunderstorms that can last for hours and produce tornadoes. These cells maintain a delicate balance between inflow and outflow, updraft and downdraft, and they can persist across vast distances, maintaining structure in the face of shifting terrain and air currents. Watching one from a distance, you don't just see clouds, you see behavior. You see something assembling, holding form, reacting to obstacles, drawing energy where it can. Again, no consciousness, but an eerie resemblance to intention. Why does that matter? Because it suggests that Earth's atmosphere isn't just a backdrop for weather, it's a responsive system. And within that system, storms behave like emergent phenomena, patterns that arise from countless small interactions, but take on a life of their own. This idea of emergence shows up everywhere in nature. Birds in a flock don't plan their flight path, but together they form shapes. Fish in a school shift directions without a leader, and storms driven by temperature, pressure, moisture, organize themselves into patterns that act, endure, and sometimes evolve. It's worth noting that our models of storm formation are still imperfect. Despite satellites, radar, and supercomputers, there are aspects of storm behavior we can't fully predict. Why some storms intensify rapidly, for example, or why some spawn tornadoes while others don't. We can map the probabilities, but the system itself contains surprises, feedback loops, subtle shifts, thresholds that once crossed change everything. And this unpredictability is part of what makes storms feel alive. Not in a comforting way, but in the way that animals are familiar yet volatile, responsive yet wild. When humans build systems, machines, software, organizations, we value adaptability. We design for feedback, for course correction, for resilience. When those systems respond to change, we call them smart. When they anticipate change, we call them intelligent. And yet here are weather systems built by physics, fed by heat, sculpted by spin, that do all of that without design. They respond, they shift course. They adjust to inputs, not to achieve a goal, but to sustain motion. Some scientists have explored the idea of storms as examples of dissipative structures, systems that maintain order by consuming energy and expelling entropy. In other words, they stay organized by burning through chaos. That's not metaphor. It's a thermodynamic principle, and it applies to living systems too. Metabolism works the same way. In this view, the boundary between life and non-life gets blurry. What makes something alive? Is it structure, self-maintenance, energy flow, reproduction? Storms don't reproduce, but they form, stabilize, regulate, and dissolve in ways that resemble life cycles. They don't have purpose, but they do have persistence. And that's what leads to the strange thought. Maybe it's not that storms are alive or that they think, but that they're part of a system that does something very close to both. The Earth's atmosphere isn't just a container, it's a medium through which energy moves, transforms, and reorganizes. And storms are one of the ways it does that. They're not accidents, they're expressions of tension, of imbalance, seeking relief. And in that process, they decide where to go, not through choice, through conditions. But the outcome looks similar, motion shaped by information, structure shaped by response. This doesn't make storms any less dangerous. If anything, it makes them more sobering. Because if storms are part of how the planet regulates itself, if they're not just side effects, but system-level responses, then disrupting the system means disrupting the patterns. And that's what we're beginning to see. Warmer oceans, more moisture in the air, more energy in the system, storms that form more quickly, move more slowly, dump more rain, cover more ground. Storms that surprise even the models built to anticipate them. The feedback are still active, the mechanisms still work, but the inputs have changed, and so the outputs are changing too. And that's a pattern we'll see again. In water, in ice, in carbon, in fire. Earth systems don't just run, they respond. And when they respond, they don't always return to baseline. Sometimes they find a new one. After following the movement of storms and the tension in the skies, it helps to return to something that seems at first glance much more still. Mountains don't shift with the seasons. They don't breathe like forests. They don't move like oceans. But that stillness is deceptive. It's not emptiness. It's storage. Mountains carry history, not in symbols or text, but in their very structure. In this way, they behave like the memory of the planet. Vast, slow, and remarkably detailed. We tend to think of memory as something tied to brains, neurons firing, experiences stored, patterns recalled. But memory can take many forms. A tree ring holds the shape of a season, a glacier captures the air of another age, and mountains through their shape, their composition, their layering carry records that span not years, but hundreds of millions of years. If you know how to read them, they tell a story, not just of what happened, but how Earth responded. Start with sediment, layers of rock that build up over time, one on top of the next. Some are the result of rivers laying down fine particles, carried from elsewhere. Others come from ancient oceans, once covering places we now think of as landlocked. Each layer holds clues, minerals, fossils, grain size, chemical signatures. A dry period leaves different marks than a wet one. Volcanic ash tells of eruptions. Charcoal layers hint at ancient fires. These aren't just scattered traces, they're organized records. Geologists call this stratigraphy, and it's one of the primary ways we study Earth's past. But the layers don't just accumulate. They also fold, break, tilt tectonic forces, pushing, pulling, sliding, bend the strata into arcs and waves, or crumple them into jagged peaks. When you see a mountain range with tilted layers of rock, you're not just seeing geology, you're seeing history compressed and reshaped. You're seeing events that happened long before humans, recorded not in ink, but in stone. Some of these records are breathtaking in scope. The Himalayas, for example, are the result of the Indian subcontinent colliding with Asia. That collision began tens of millions of years ago, and continues today. As the plates push against each other, the crust rises, but it also traps within it rocks that were once at the bottom of the sea. Marine fossils high on mountain slopes show us that what is now the world's tallest range was once submerged. The mountain remembers the ocean. The Appalachian Mountains in North America are older still, formed hundreds of millions of years ago, during the assembly of a supercontinent called Panga. They've eroded over time, but their roots remain. And in those roots, we find evidence of the Earth's earliest tectonic movements. The memory there is not just long, it's foundational. It's the memory of how continents came to be. Then there are the volcanoes, mountains that don't just remember the past, but actively shape the future. Volcanic layers can record cycles of eruption and dormancy. Some eruptions leave behind pumice and ash. Others deposit thick lava flows that cool into basalt. The chemistry of these materials tells us about the composition of the Earth's mantle at different times. And the gases trapped in volcanic rock offer clues about ancient atmospheres. In Iceland, in Hawaii, along the Pacific Ring of Fire, volcanoes serve as outlets for the planet's internal processes. They release pressure, redistribute material, alter landscapes, and in doing so, they write new layers into the geologic record. They remember not by storing, but by transforming. Even the shape of a mountain range carries information. Sharp peaks suggest youth, recent uplift, minimal erosion. Rounded hills suggest age, long exposure to wind, rain, freeze. Thor glacier-carved valley tells of ice that once covered vast stretches of land. The scars are still visible like wrinkles in the skin of the Earth. And it's not just rock. Ice, too, becomes part of the mountain's memory. Glaciers trap air bubbles as they form. Those bubbles contain traces of greenhouse gases, carbon dioxide, methane from times long. When scientists drill ice cores in mountain glaciers, they can read climate data stretching back hundreds of thousands of years. Temperature, precipitation, atmospheric chemistry. It's all there, frozen, quiet, waiting to be understood. What's remarkable is that these records not just passive, they don't just sit there, they influence what comes next. The shape of a mountain affects how wind moves, where rain falls, how rivers flow. Those rivers carry sediment, which forms new layers elsewhere. Snowacks determine the water supply for ecosystems downstream. The mountain's memory shapes the valley's future. This kind of influence, slow, indirect, persistent, is easy to miss. It doesn't announce itself, but it's critical. Mountains help regulate climate. High elevations reflect more sunlight. Snow cover cools the air. Alpine ecosystems respond quickly to changes in temperature. They're like early warning systems, alerting us to shifts in the broader system. And now many of those systems are changing. Glaciers are retreating. Permafrost is thawing. Rock faces once locked in place are beginning to shift, triggering landslides. The mountain is still remembering, but the pace of change is accelerating, and in some cases, the memory is being erased. Mining, deforestation, construction, these don't just alter the mountain surface, they remove layers, they disturb strata, they blur the record, and when the record is blurred, we lose our ability to understand not just what happened, but how Earth adapted before. We lose reference points. We lose context. This is one of the stranger consequences of living on a planet with memory. We can learn from it, but we can also damage it. Not just ecologically, but historically. The Earth is willing to share what it knows, but only if the evidence remains. It's worth pausing on that idea. A mountain, by its nature, is durable. It lasts longer than civilizations, longer than species. But that durability hides fragility, not in the rock, but in the record, the arrangement, the layering, the subtle patterns. Those are easy to disturb, and once disturbed, they don't return. So when we think about Earth as something that might be alive, or at least something more than inert, it helps to include the possibility of memory, not fast memory, not deliberate memory, but something like accumulation, something like structure, a past that influences the present, not through thought but through form. We see this in biology too. A scar is a kind of memory. Bone density changes in response to stress. Immune systems adapt to threats. Bodies remember even when we don't ask them to. Maybe the planet does too. Maybe mountains are part of how that memory is stored. Not in one place, but across landscapes, across time. It's not that the mountain thinks, but it knows what happened. Not in words, but in weight and shape and layer. Continuing the idea that mountains remember, and that the planet might hold its history in forms deeper than speech, we arrive at a question that's quieter, but just as strange. If the Earth were aware in some way, how would it communicate? And would we even know how to listen? Language, as we use it, is a tool for transmitting meaning. It's structured, symbolic, and usually verbal. But that's not the only kind of communication. The natural world is full of messages. Signals passed from one part of the system to another, not with vocabulary, but with chemistry, movement, frequency, and timing. When we start to look at these interactions closely, we find that life on Earth is constantly talking, just not in ways we were taught to recognize. Plants, for instance, don't have mouths or ears, but they respond to touch, light, temperature, gravity. They bend toward the sun. They close their leaves when touched. They send chemical warnings when injured. In some cases, when a leaf is bitten by an insect, it releases volatile compounds that drift into the air. Nearby plants detect those compounds and activate their own defensive chemicals. It's not noise. It's not random. It's signaling. This kind of airborne messaging doesn't happen just within species. Some plants warn others. Some attract helpful predators, tiny wasps, for example, that prey on the insects eating them. It's indirect, but it's purposeful. A plant in distress doesn't shout, it emits. Underground, the signals continue. Roots release chemicals into the soil, shaping the microbial communities around them. Different plants can recognize relatives and adjust their root growth accordingly. Some avoid competition, some seek collaboration, and all of it happens without words. Fungi, as we've seen, form vast networks in the soil that connect plant roots. Through these networks, nutrients and signals pass. It's not always clear what's being said, but changes in one part of the system cause responses in another. The information moves, and that's the core of any language. Animals, of course, have many forms of communication. Birds sing, whales call, bees dance, but even beyond the obvious, there are layers. Bats use echolocation. Elephants communicate with low-frequency sounds that travel underground for kilometers. Some species of fish change color to signal readiness to mate or to warn off predators. Octopuses pulse and ripple patterns across their skin, not just for camouflage, but to convey intent. Each of these signals is adapted to the environment, and each relies on a receiver who can interpret it. That's what makes it language-like. It's not just expression, it's expression meant to be understood. And this is where it gets more interesting, because many of these signals aren't deliberate in the human sense. They're evolved responses, automatic, reflexive, tuned over time, but they still function. They still transmit. And that raises the question, how much communication in nature happens without intent? Think of your own body. Your cells talk constantly. Hormones carry messages through the bloodstream. Neurons fire across synapses. Your immune system coordinates attacks on invaders. You don't think those thoughts, but they still happen. The system functions through signaling, and signaling creates response. No words required. So if Earth as a whole is a system, a web of interacting parts, it follows that communication might happen at scales we don't notice, not centralized, not conscious in the way we are, but present. Take the atmosphere. Changes in ocean temperature cause shifts in air pressure, which influence jet streams, which steer storms. The information moves not through syntax, but through cause and effect. The system reacts. Parts influence other parts. The behavior propagates. Or consider fire. In some ecosystems, fire is not just a threat, it's a message. Certain plants only germinate after a burn. The heat triggers growth. The smoke stimulates flowering. Over generations, species have adapted not just to fire, but to the timing of fire, the rhythm of renewal. They listen in their own way for the right conditions, for the signal. Even microbes talk. Quorum sensing is a process by which bacteria detect the presence of others by releasing and detecting chemical signals. When the population reaches a certain density, the group changes behavior. It becomes more virulent or more cooperative, or it moves. It's a basic form of consensus, not with votes, with molecules. This kind of signaling shows up in coral reefs too. Coral polyp communicate with the algae that live inside them, maintaining a relationship that sustains the entire reef. When conditions become stressful due to heat or pollution, the relationship breaks down. The coral expels the algae, leading to bleaching. It's a collapse in communication. And when it happens at scale, the whole system starts to fail. So much of what we depend on relies on these quiet chemical languages, the release of pheromones, the shift in wavelength, the pattern of movement. They're not metaphorical, they're functional, and they can be disrupted. Pollution, noise, artificial light, all of it can drown out or confuse the signals that keep ecosystems stable. This matters because communication in the broadest sense is what allows systems to regulate themselves, to maintain balance, to avoid collapse. When the signals stop, feedback breaks down, and when feedback breaks down, systems lose their ability to adapt. You can think of it like a conversation in a crowded room. If the signal is clear, responses are fast and relevant. If the noise gets too loud, the conversation stops making sense. Miscommunication becomes more likely, and eventually coordination fails in the biosphere. We're starting to see that shifts in phenology, the timing of biological events, are throwing off interactions. Flowers bloom earlier, but the insects that pollinate them arrive late. Birds migrate to find food that's no longer there. The signals are still being sent, but they're out of sync. And when rhythms lose alignment, the system stumbles. None of this is new to nature. Ecosystems have always adapted to change, but the pace matters. When change happens gradually, communication evolves with it. When it happens quickly, signals get crossed, and the system doesn't have time to learn. So when we talk about Earth as possibly being aware, not in a mystical way, but in a systems-based way, we're really talking about this: the ability of parts to interact, to signal, to coordinate. That's what makes an organism more than just a pile of cells. That's what makes a society more than just a collection of people. Earth as a whole may not have a single voice, but it's full of messaging. Signals moving from root to sky, from sea to cloud. Networks that relay information. Responses that shape the conditions for life. If that's not language, it's at least something adjacent. Something that serves the same function. It's a reminder that communication doesn't begin with words. It begins with response. And Earth responds constantly across scales, across media, across time. We now look upward, not just at the clouds or the movements of weather, but at the sky itself. Not the poetic version, but the physical one. A layer of atmosphere hundreds of kilometers deep, clinging to a spinning planet, filled with particles, currents, fields, radiation, and light. It's easy to see it as emptiness, a space we pass through, a barrier between ground and stars. But it's more than that. The sky is active, structured, reactive, and for all its apparent vastness, it pays very close attention. It watches not in the conscious way we do, but through constant adjustment, through reflection, refraction, absorption, through regulation of what comes in and what goes out. And it does this in ways that affect every living thing below. Start with sunlight. Every second the Earth is bombarded by solar radiation, visible light, ultraviolet, infrared, and beyond. Most of it is harmless, some of it essential, and some of it dangerous. The sky doesn't block all of it, but it filters. The ozone layer, for example, sits high in the stratosphere and absorbs the majority of the sun's harmful ultraviolet radiation. Without it, the surface would be hostile to most forms of life. But that layer didn't always exist. It was formed over time, shaped by the presence of life, specifically by photosynthetic organisms that released oxygen into the atmosphere. That oxygen eventually led to ozone. So in a very real way, life created the conditions that shield life, a feedback loop, an atmospheric response to biology. And this feedback continues. Clouds reflect sunlight back into space, cooling the surface. Greenhouse gases trap heat, warming it. Particles from volcanoes or dust storms can brighten or darken the sky, changing the balance. The atmosphere doesn't just sit there. It mediates energy flow. It takes information from the ground, the oceans, the forests, and responds with changes in temperature, pressure, humidity, and wind. These responses don't happen uniformly. The sky behaves differently over ice than over desert. It shifts patterns depending on vegetation, on ocean temperatures, on the albedo of different surfaces. It's not a one-way system. It's a conversation. Signals go up, conditions come down. And the signals it receives aren't only natural anymore. Human activity now emits vast quantities of aerosol, soot, methane, carbon dioxide, water vapor. These particles interact with sunlight and cloud formation. They change the chemistry of the air. They influence when and where rain falls. They even alter the color of sunsets. The sky records this, not with memory as we know it, but with measurable change. Satellite data shows it clearly. Heat maps, color shifts, alterations in reflectivity, zones of pollution, even small changes in land use, clearing a forest, draining a wetland, building a city, send signals into the atmosphere. These signals don't disappear, they spread. They shape jet streams, monsoons, droughts. The system pays attention. And there's more than light and heat. Earth's magnetic field, generated by its spinning molten core, extends outward and interacts with the solar wind, a stream of charged particles from the sun. This interaction creates the magnetosphere, which deflects most of the harmful solar radiation. It also creates auroras near the poles, dancing lights in the upper atmosphere caused by particles crashing into molecules of oxygen and nitrogen. Those lights are beautiful, but they're also functional. They show the system adjusting in real time, regulating energy from beyond the Earth, keeping balance. Even lightning has its part. Beyond its role in storms, it helps maintain the electrical balance of the atmosphere. Every day, thousands of strikes discharge built-up static, moving charge between the sky and the ground. And some studies suggest that lightning may play a role in fixing nitrogen into a form usable by plants, feeding the biosphere in an indirect but meaningful way. The sky watches chemically too. Sensors placed high above the Earth have detected shifts in atmospheric composition that correspond not just with large-scale events like volcanic eruptions or wildfires, but with changes in microbial activity in the soil, deforestation rates, even seasonal plant growth. The exhalations of life reach the sky, and the sky shifts in response. There are signs we're only beginning to understand. Gravity waves ripple through the atmosphere after massive disturbances. Temperature inversions trap pollutants in valleys. Clouds form at just the right altitude and droplet size to reflect or absorb heat. These aren't just weather patterns. They're information carriers. real-time responses to real-time changes. Some researchers have described the atmosphere as a thin dynamic membrane that regulates planetary energy. It's only a few dozen kilometers thick, less than the distance between two cities, but it contains almost everything that breathes, flies, rains, or burns. And within that thin layer, Earth maintains its livable state. When seen from this perspective, the sky is not a passive space. It's a balancing act. Every molecule of gas, every drop of water, every gust of wind contributes to a kind of ongoing measurement. Inputs are constantly weighed. Heat, moisture, pressure, chemistry, and outputs are constantly generated. Clouds, storms, jet streams, calm. And when the inputs change faster than the system can adapt, the sky responds accordingly. It doesn't restore what was, it adjusts to what is. And that adjustment can be gentle or violent, prolonged drought, unexpected hail, longer, slower hurricanes, weather that feels unfamiliar, not because the sky is failing, but because it's recalibrating to a new set of conditions. This is important because we often treat the atmosphere as separate. We dump into it, extract from it, rely on it, without thinking of it as something that responds. But it does, and the more we understand it, the clearer it becomes. The sky is not a void, it's a participant, a sensor, a regulator. You could say it watches, not in the way an eye watches, but in the way a sensor array tracks change, the way a thermostat notices heat, the way a system designed to preserve balance notices imbalance. And in that sense, the sky is one of the planet's most responsive systems. It's the first to shift when conditions change. It's the first to warn when thresholds are crossed. And it's the first to send feedback, whether through temperature, turbulence, or silence. It doesn't speak, but it signals. And we've learned slowly how to listen. Weather balloons, radar, satellite instruments, LAR, chemical sensors, all tools we've built to interpret what the atmosphere is telling us. Not just forecasts, but clues about the deeper state of the Earth's system. Because when the sky changes, something larger is changing too. If all these systems, oceans, forest, soil, storms, even the sky respond to change, regulate themselves, and interact across vast scales, what exactly separates this planet from something we would call alive? And if it's alive in any meaningful sense, is it conscious? The word consciousness is tricky. It comes with a lot of assumptions. Most people think of it in human terms: awareness, thought, identity, memory. But in biology and neuroscience, consciousness doesn't always mean self-reflection. Sometimes, it just means the capacity to integrate information and respond coherently to a changing environment. Something that senses and then does something about it. Under that broader definition, the idea of a conscious Earth doesn't feel as strange, especially when you look at how we define consciousness in other animals. Humans aren't the only species with awareness. Elephants recognize themselves in mirrors, octopuses solve puzzles and show signs of individual personality, birds plan for the future, some monkeys mourn their dead, even insects demonstrate forms of learning and preference. The deeper we look, the harder it is to draw a clear line between conscious and not. In neuroscience, there's no single agreed-upon seat of consciousness. We know it involves networks, circuits of electrical activity across the brain, that light up, synchronize, desynchronize, repeat. But what's more important than the individual neurons is the way they connect, the pattern of interaction, the integration of signals into a single state that represents the organism's experience. This idea has led to theories like integrated information theory, IIT, which suggests that consciousness arises from the level of interconnectedness in a system, not just the number of parts, but the richness of their interactions, how much influence one part has on the whole, and how well the system can differentiate between different states. Under that framework, consciousness is a gradient, not all or nothing, more like a spectrum. Systems with more complex, high integrated information would have higher degrees of consciousness. Systems with simpler structures would have less. And that brings us back to Earth. Because when you step back and look at it, not as a collection of parts, but as a single system, it's hard to ignore how complex and integrated it really is. Every biome affects the others. Every system has feedback. Changes in one domain ripple into the next. Nothing is truly isolated. The ocean influences the atmosphere, which influences forests, which influence soil, which loops back into the climate. When scientists model these systems, they often find tipping points, critical thresholds where a small change causes a large-scale shift, and to avoid those shifts, the planet maintains buffers, forests that cool the air, wetlands that absorb excess rain, ice caps that reflect sunlight, each part adjusting to stabilize the others. This is more than equilibrium, it's active balancing. We call this homeostasis in biology, the ability of an organism to maintain stable internal conditions despite external changes. Your body does this all the time. You sweat when you're hot, you shiver when you're cold. Blood sugar, pH, heart rate, everything adjusts constantly and you don't think about it. It just happens. The Earth shows signs of homeostasis too. Not perfectly, not instantly, but it responds. When carbon dioxide rises, oceans absorb more. When heat increases, clouds shift. When ecosystems damaged, others adapt. Sometimes the responses are overwhelmed. But the attempts are there. This kind of regulation raises the question, does it require consciousness? Not necessarily. A thermostat can regulate a room's temperature without being aware of anything. But when regulation happens across dozens of interconnected systems, each influencing the others, it becomes harder to dismiss the comparison. Not because the Earth has a brain, but because it behaves like a system that knows how to keep itself going. And that's where the idea of planetary consciousness enters the conversation. Not consciousness as thoughts or feelings, but consciousness as responsiveness, as presence, as a system that's more than the sum of its parts. This idea has appeared in many forms over time. In ancient cultures, Earth was often viewed as a living being, Dia to the Greeks, Pachamama to the Andean peoples, not as metaphor, but as reality, a being that feeds, breathes, hurts, heals. Modern science moved away from that idea, favoring mechanisms over meaning, but now, in some corners, it's returning, not out of mysticism, but out of observation. The Gaia Hypothesis, proposed by James Lovelock and Lynn Magulus in the 1970s, suggested that the biosphere and physical environment form a complex self-regulating system, one that maintains conditions favorable to life. At first, the idea was controversial, too speculative, too anthropomorphic, but over time, aspects of it gained traction, especially as evidence of planetary-scale feedback loops began to accumulate. Critics point out that regulation doesn't imply intention. The planet isn't choosing to keep itself habitable. It just happens that life has evolved to support the conditions life needs. But even if that's true, it still describes a system that acts, reacts, and adapts on a global scale, which in some ways is what we do when we're conscious. So maybe the Earth isn't conscious in a personal sense. It doesn't dream or decide, but maybe it's conscious in a systemic sense, aware of itself through feedback, responding to internal and external pressures, evolving over time. And maybe consciousness doesn't have to look like ours to be real. There's also the question of time. Our own awareness operates on fast scales, seconds, minutes, days. We measure awareness by reaction speed, but what if consciousness could be slow? What if it unfolded over decades, centuries, millennia? Would we even notice it? If the Earth has a form of awareness, it might not be something we can detect in real time. It might show up as long patterns of adaptation, slow pulses of balance and imbalance, cycles of expansion and retreat, intelligence without urgency. This is not a theory with a testable outcome, at least not yet, but it's a shift in how we frame our relationship to the planet, not as residents on a rock, but as participants in a vast, ongoing system that responds to itself. Some researchers have begun exploring the idea of planetary intelligence, not as a New Age belief, but as a scientific model. They ask what it would mean for a planet to process information across scales, to store, transmit, and integrate that information, to develop feedback systems that optimize for long-term stability, not as a conscious plan, but as an emergent outcome. By that logic, humans might not be the mind of the Earth. We might be one part of a larger process, part of the sensing, the memory, the disturbance, the adaptation, sometimes helping the system, sometimes hurting it, but never outside it. Which leads to a final question, not about the Earth, but about us. If Earth is in some way conscious, or even just responsive, what is our role in that system? Are we signals? Are we noise? Are we antibodies? Are we disease? Do we enhance the planet's awareness, or do we distort it? There may not be a clear answer, but maybe the better question is this. What would change if we acted as if the planet were conscious? Not out of certainty, but out of respect. Because if something watches, responds, remembers, and adapts, it might not matter whether it's aware in our terms. It might still deserve to be treated like something that is. We narrow the lens now, not to lose the big picture, but to examine the smallest and most familiar parts of it. The lives we tend to notice, the ones most like us, or most unlike us, the ones with eyes, with movement, with choices, mammals, microbes, and the long chain of meaning that runs between them. On the surface, these categories don't seem connected. One is tiny, mostly invisible, the other warm-blooded, large, mobile, and yet both play roles in the broader pattern of life on Earth that extend far beyond their size or complexity. Both participate in something larger than themselves, systems that shape, regulate, and sometimes even define the conditions of the planet. Start with microbes. By sheer numbers, they dominate. In every drop of ocean water, in every inch of soil, inside our bodies, on the edges of volcanoes, deep in the crust, microbes persist, not just as passive passengers, but as drivers of planetary function. The oxygen we breathe was first produced by photosynthetic bacteria. The nitrogen in the soil is fixed by microbial communities. The decay of matter, the cycling of nutrients, the fermentation of food, the defense of our immune systems, none of it would work without them. We think of intelligence as something that needs a nervous system, but microbes communicate chemically, adapt quickly, respond to threats, and evolve at astonishing speeds. In colonies, they behave collectively. In biofilms, they form protective layers. Some can lie dormant for decades and awaken when conditions improve. Some can even exchange genes directly, a kind of lateral information sharing that looks in many ways like learning. On a planetary scale, their effects are foundational. Microbes in the ocean, specifically phytoplankton, carry out nearly half of the photosynthesis on Earth. They form the base of the marine food web. They influence climate by sequestering carbon and producing cloud-seeding compounds. When their populations shift, so do weather patterns. Microbes in the soil interact with plant roots, not only helping plants absorb nutrients, but also protecting them from pathogens. These networks, invisible to the eye, form a kind of silent economy beneath every forest, every farm. They decide what grows and what doesn't. And all of this happens without our awareness. These organisms don't announce themselves, but their influence is everywhere. They are, in a sense, the nervous system and metabolism of the biosphere. Mammals, by contrast, are the ones we recognize, not just because we're mammals ourselves, but because they exhibit behaviors that mirror our own. They nurture their young, they form social bonds, they explore, migrate, adapt, from elephants that grieve to whales that sing, to primates that use tools. Mammals demonstrate awareness not just of their environment, but of each other. They're not the only animals with complex behaviors, but we tend to focus on them because of their eyes, their expressions, their voices. We empathize, we assign meaning to their actions, and in doing so, we reveal something about ourselves. We look for meaning in similarity, but what if meaning isn't limited to resemblance? What if it's embedded in relationship? Because mammals, too, shape their environments. They alter landscapes through grazing, burrowing, building. They spread seeds, control populations, support ecosystems. Beavers dam rivers and create wetlands. Wolves regulate the behavior of prey and indirectly the growth of forests. Bats pollinate plants and control insect populations. Humans, uniquely disruptive, reshape the entire planet. We often speak of humans as separate from nature, but from a systems perspective, we're participants, not outside observers. The choices we make affect the same loops of feedback and regulation as any other species. We burn fuel, change the composition of the atmosphere, alter the albedo of the surface. We divert rivers, mine minerals, breed plants, build cities. We are a force, not because we're above the earth, but because we are embedded in it. And like microbes and other mammals, we operate in patterns. Our societies evolve, our technologies replicate, our knowledge spreads laterally. In many ways, our behavior as a species resembles biological processes at other scales, not metaphorically, but structurally. So the question becomes, what does this behavior mean? What is the significance of all this activity, these interactions across scales? Meaning in a biological sense isn't always about purpose. It's often about function. What role does something play? What impact does it have? In that light, microbes give meaning to death by breaking down the dead into usable matter. Mammals give meaning to movement by distributing life across landscapes. And humans at our best have the potential to give meaning to awareness itself. Because we're not just reactive. We observe, we reflect, we model systems in our minds, we imagine futures, we measure, simulate, and sometimes, though not always, adjust based on those simulations. We are perhaps the first species with the ability to consciously respond to planetary feedback to decide what kind of influence we want to be. But that awareness is a double-edged. It allows us to solve problems. It also allows us to ignore them. We can sense the warming atmosphere, the dying reefs, the collapsing forests, and still do nothing. No other species does this. No other species has to. So meaning for us becomes a choice. And that choice extends not just to what we value, but to how we see ourselves in the system. Are we the top of the chain, or a node in the network? Are we architects of Earth's future, or stewards of its balance? Are we immune to feedback, or shaped by it? This isn't a moral question, it's a practical one, because every living thing participates in cycles larger than itself. Microbes break down what mammals leave behind. Mammals move what microbes build. Together, they sustain the systems that keep the planet habitable. We sit at the intersection of those systems, able to observe both ends of the scale, able to influence both, and what we do with that ability may determine how long the cycles continue as we've known them. Meaning doesn't have to be abstract. It can be grounded in structure, in behavior, in continuity. And in that sense, the planet's meaning, if it has one, is found in the persistence of life, in the ability to adapt, respond, and renew. And every organism, from the smallest bacterium to the largest whale, contributes to that persistence. We're part of that contribution too. We always have been. It becomes harder to separate what is alive from what simply endures. And there's one system in particular that seems the furthest from life, the slowest, the most indifferent, the motion of continents, the shifting of plates, the gradual cracking, folding, and reshaping of the Earth's crust over hundreds of millions of years. It feels geological. It feels outside the question of awareness. But when you look closely, the behavior of plate tectonics suggests something more. Not thought, not purpose, but something like deep responsiveness, something like memory, something like dreaming. Plate tectonics is the movement of large slabs of Earth's lithosphere, the rigid outer shell floating at top the softer, hotter mantle. The crust isn't one unbroken surface. It's fragmented into plates, some oceanic, some continental, and they move, not by much, just a few centimeters per year. But over time, they redraw the map of the planet. These motions aren't random. They're driven by processes in the Earth's interior, convection currents in the mantle, the pull of sinking slabs, the heat from radioactive decay. But the effects on the surface are profound. Mountains rise, oceans widen or close, continents break apart and later rejoin, volcanoes erupt, earthquakes ripple, and all of it happens in slow looping cycles. This is how the Himalayas formed as India pushed into Asia. It's how the Atlantic Ocean opened as Europe and North America drifted apart. It's how subduction zones form trenches and island arcs. Over time, land becomes sea. Seabed becomes summit. The planet turns itself inside out. It's easy to see this as mechanical, a slow planetary churn, but patterns emerge over the last billion years. Supercontinents have formed and broken apart multiple times. Rodinia, Pannotia, Gondwana, Pangaea, each followed by stretches of isolation, climate shifts, and new bursts of biodiversity. The breakup of Pangaea, for example, led to isolated environments that allowed species to evolve separately. That motion helped shape the diversity of life we see today. In that sense, plate tectonics is not just a background process. It's a shaper of possibility. Its slow shifts rearrange ecosystems, change ocean currents, and influence global temperatures. Volcanic eruptions release carbon dioxide, mountain ranges alter wind patterns, plate boundaries mark zones of extreme richness geologically and biologically, and these shifts happen with rhythm, not a clockwork rhythm, but a loose cycle, patterns of assembly and dispersal, collision and retreat. It's not always smooth. Plates stick, then slip. Earthquakes release pressure. Magma rises, then settles. But over time, the surface of the planet reconfigures itself in repeating themes. Some scientists study these cycles not just as historical curiosities, but as essential to the Earth's habitability. Plate tectonics helps regulate the carbon cycle. When volcanoes erupt, they release CO2. When rocks weather, they absorb it. Subduction carries carbon sediments into the mantle where the process begins again. Without this cycle, greenhouse gases would build up unchecked or vanish entirely. The climate would drift out of balance, and unlike most known planets, Earth has maintained the cycle for billions of years. Mars once had tectonic activity, but it stopped. Venus has signs of resurfacing, but not plate tectonics as we know it. Earth so far seems unique. Some researchers argue that plate tectonics functions as a planetary thermostat, not perfectly, not quickly, but over long spans of time. It helps maintain temperatures that allow water to remain liquid and life to persist. It's a feedback system, not for days or years, but for epochs. And if that's the case, it raises the same question again. What kind of system behaves like that? One with regulation, one with feedback, one that adapts. This doesn't mean the planet is alive in a biological sense. Tectonic plates aren't cells. Faults don't think. But the system as a whole maintains conditions that support life, and it responds to imbalance. Maybe not deliberately, but effectively. And then there's the metaphor. Not just the literal process, but what it suggests. Plate tectonics is incredibly slow. Its changes are mostly invisible over a human lifetime, and yet it is always happening. Cities rise and fall on plates that move. Mountain ranges grow a few millimeters each year. Trenches deepen. Islands migrate. The whole surface of the planet rearranges itself quietly underfoot, and it starts to resemble something familiar. Not movement we can see, but movement we can trace. Movement that reveals itself in hindsight, like a dream. Slow, symbolic, shaped by forces we don't fully understand until long after the fact. In dreams, our minds replay, reorganize, resolve. They filter through what we've experienced, sometimes incoherently, sometimes meaningfully. And while the content may seem chaotic, the act of dreaming has purpose. It maintains the system. It balances memory, emotion, learning. What plate tectonics does for the planet isn't that different. It reorganizes the surface. It balances pressure. It releases energy. It buries and resurrects. It turns stress into structure. And just as dreams influence waking life, tectonic motion influences everything above it. Not directly, not instantly, but persistently. The shape of the continents affects rainfall. The depth of oceans affects heat circulation. Even the tilt of the Earth, its axis, its seasons can be influenced by the distribution of mass at the surface. So what happens below doesn't stay below. The crust is not a shell. It's a membrane in motion. This perspective doesn't require mysticism. It requires systems thinking. The recognition that what seems separate is often connected. That slow processes still matter. That change doesn't have to be visible to be real. And in that framework, plate tectonics becomes part of the Earth's overall regulation, a mechanism that both records history and sets the stage for what comes next. The scars of past collisions remain. So do the trails of old rift zones, the ghosts of vanished oceans, the buried edges of continents lost to time. The planet remembers, not in words, but in position. Not in thoughts, but in shape. And that memory isn't passive. It folds into the future. It directs where the next mountain will rise, where the next quake will release, where the next sea will open. Just as we dream in symbols, the Earth may dream in pressure and fracture, in uplift and descent, in the slow movement of heat and stone, a kind of long geologic imagination, reshaping itself over and over. And like any dream, the meaning may not be clear until later. We live on the edge of something vast, a crust that moves, breathes heat, and reforms itself in silence. If Earth could speak, what would it say? Not in metaphor, not as myth, but seriously. If all these systems, oceans, forests, soils, clouds, plates, are constantly interacting, measuring, responding, and remembering, then the planet is already expressing itself. Not through voice, but through consequence. Not through language, but through signals. What we mean by speak is usually some structured act of communication, sounds organized into patterns intended for another to interpret. But as we've seen in forests warning each other through roots and fungi, in microbes trading chemical messages, in clouds forming in response to particles, Earth already transmits messages. The problem is never whether the Earth is talking, it's whether we're listening in the right way. Start with temperature, the rising average, the heat waves growing longer, more frequent, more deadly. These aren't isolated events. They're a kind of speech, feedback from a system absorbing more energy than it's able to reflect. The glaciers melting, the sea levels rising, the droughts extending. Each one is a line in a conversation we've been ignoring for too long. When we deforest, the water cycle changes. Less transpiration, less rainfall, drier soil. The Earth responds. Crops fail, rivers shrink, fire seasons stretch. It doesn't issue warnings, it just shifts. It delivers outcomes. When the atmosphere thickens with carbon, it holds more heat and the jet stream weakens. Weather stalls. Rain falls in the wrong places, or all at once. The Earth adjusts, not out of intent, but necessity. It rebalances using the only tools it has: energy, mass, motion. You could call these responses mechanical. You could call them chemical, physical, inevitable. But if they consistently follow action with reaction, if they deliver information back to the origin point, then they serve the same function as communication. The message is something has changed. The tone is adapt. If Earth could speak in ways we'd understand, it wouldn't sound like us. It wouldn't form sentences or declare its intentions. It would map pressure gradients across the sky. It would shift the timing of monsoons. It would raise sea temperatures enough to bleach coral reefs and collapse fisheries. And in a sense, it already does all of that. We just haven't wanted to call it speech. Because once you admit the planet is speaking, you have to decide how to respond. When volcanoes erupt, they inject aerosols into the stratosphere, cooling the planet for years. Not as punishment, as physics. When ice melts, it darkens the surface, which absorbs more heat. That's feedback, a loop, a sentence with a subject and effect. And when entire ecosystems begin to falter, the Earth speaks again through extinctions, migrations, trophic cascades. Wolves disappearing changes the rivers. Insects disappearing changes the birds. It's not symbolic, it's structural. Meaning through connection, we often expect messages to come with warning signs, lights flashing, voices raised. But many of Earth's clearest messages come quietly. A shift in pH in the ocean, a missing bloom of phytoplankton, a change in the soundscape of a forest once filled with insects and frogs. We hear less, we notice less. The message still is being sent. Some scientists call these tipping points, not because the Earth tips, but because once crossed, the system moves into a different state, like a fever or a threshold. The voice becomes harder to ignore, the symptoms spread, and what's strange is how consistent the Earth's messages have been. Rising CO2 correlates with warming, deforestation correlates with declining rainfall, overfishing leads to collapse. None of this is secret, none of it is subtle. It's a voice shaped by pattern, and the patterns are repeating. If we treated this as a kind of conversation, we might ask different questions. Instead of just measuring what's changing, we'd ask why the system is responding the way it is. Instead of debating whether Earth is alive, we might ask what it's trying to stabilize. And instead of seeing ourselves as spectators, we'd realize we've been in dialogue the whole time. The Earth speaks in systems, and we're one of them. Our cities, our agriculture, our industries, they've become major participants in the planetary loop. What we emit, what we remove, what we alter, all of it feeds back into the same conversation. And the planet answers, not in anger, but in consequence. This doesn't require belief, just observation. The same way we track symptoms in a body, we can track symptoms in a biosphere. Fever, inflammation, fatigue, imbalance. These aren't judgments, they're indicators. And that means we also have the chance to shift the conversation, to change the signals we send to, participate in repair. When forests regrow, temperatures stabilize. When emissions drop, the air clears. When biodiversity returns, resilience follows. Earth listens as well as it speaks. Not in real time, but over time, it adapts. It integrates. It adjusts. Not because it's forgiving, because that's what systems do when they still have flexibility, But that flexibility has limits, and part of listening well is knowing when silence is no longer an option. If Earth could speak, maybe it would ask, "Are you hearing me now?" Continuing from the question of Earth speaking through systems and signals, we arrive at one of the clearest, coldest voices the planet has ever used: ice. It doesn't speak in words or warnings. It speaks in retreat, in cracking sounds that echo across valleys, in meltwater rushing through ancient blue veins that were never meant to open. Ice doesn't just reflect light, it reflects change, and in recent decades, it has become one of Earth's most urgent messengers. For most of human history, we thought of ice as permanent. The glaciers, the poles, the frozen peaks, they seemed immovable, too vast, too solid, too slow to change. And in the short window of human generations, that seemed true. The great ice sheets of Greenland and Antarctica had been there for hundreds of thousands of years. The mountain glaciers in the Alps, the Andes, the Himalayas, many formed before agriculture even began. They were constants in a world of change, but constants can shift, and over the past century, they've been shifting fast. It starts with temperature, just a degree or two warmer, barely noticeable to most people. But in the coldest parts of the planet, a few degrees make all the difference. Snow that used to accumulate begins to melt. Glaciers that once held firm begin to slide. Permafrost begins to thaw, not just at the surface, but knee-deep. Satellite imagery shows the pace. Glaciers that covered valleys in the 1980s now barely reach halfway. Ice shelves, once thought stable, collapse in days. Lakes form on the surface of ice sheets, absorbing sunlight, melting downward, carving tunnels through ice that used to be solid from top to bottom. In Greenland, meltwater flows to the base of the ice sheet, lubricating the rock, speeding up the flow of ice toward the ocean. In Antarctica, warm ocean currents undercut the ice from beneath, hollowing it out from the bottom. It's not a steady melt, it's a process of structural weakening, and once certain thresholds are crossed, the collapse accelerates. The ice is talking in its absence, in its sudden movement, in the shock of its silence. Scientists studying ice cores, long cylinders drilled from deep within glaciers, can read the past. Trapped air bubbles contain snapshots of Earth's faint atmosphere going back hundreds of thousands of years. They show patterns of carbon dioxide and methane, of past temperature swings, of volcanic eruptions and dust storms, and abrupt climate shifts. The record is clear. When greenhouse gases rise quickly, ice responds. The planet warms, the glaciers retreat, sea levels rise. These are not isolated events. They are chapters in a long story of balance and imbalance. But what's different now is the pace. In the past, transitions happened over thousands of years. Now, many are happening in decades. We are living inside a shift that would normally unfold over geological time, and the ice is not keeping quiet about it. It speaks in metrics. Greenland loses over 250 billion tons of ice each year. Antarctica's net loss is accelerating. The world's glaciers are shrinking in volume nearly everywhere, and sea levels have already risen more than 20 centimeters in the last century, with the rate of rise increasing. But ice speaks in subtler ways too. When permafrost thaws, it releases methane, a greenhouse gas far more potent than carbon dioxide in the short term. Frozen millennia, this organic matter begins to decompose, and the gas escapes. This adds more heat to the atmosphere, which thaws more permafrost, which releases more gas. It's a feedback loop, and it's happening now, especially in the Arctic. The thaw also affects infrastructure. Roads buckle, buildings sink, pipelines rupture, ecosystems shift, species migrate northward or vanish entirely. What was once locked in place is now on the move. Glaciers feed rivers. When they melt too fast, floods happen. When they're gone, drought follows. In parts of Asia, South America, and Africa, hundreds of millions rely on meltwater from mountain glaciers for drinking water and agriculture. As those glaciers shrink, the future of those regions becomes uncertain, not in theory, but in supply. When the ice talks back, it doesn't argue, it reflects. Polar bears wander farther, unable to hunt. Penguin colonies collapse as nesting grounds vanish. Fish populations shift with water temperature, throwing entire food chains out of balance. None of this is about the ice alone. It's about what the ice is tied to, because cold regions regulate heat, They reflect sunlight, circulate air, anchor ocean currents. The difference between ice and open water is not just visual, it's thermal. Ice reflects. Water absorbs. As sea ice disappears, the planet warms faster. Another loop, another signal. It's tempting to think of ice as passive, inert, but it moves, it breaks, it shatters, it reshapes coastlines and rearranges the weight of the planet. As ice melts and redistributes, the crust itself lifts, a slow rebound from the pressure it used to bear, and ocean currents shift in response to the influx of fresh water. The Gulf Stream weakens, monsoons change course, rain falls in different places at different times. The Earth is responding to itself, and ice is one of its key feedbacks, one of its clearest expressions. Not because it means to be, but because it can't help it. There are still people who say that climate change is invisible, too slow, too abstract. But anyone who listens to the ice knows otherwise. The visibility is rising, the abstraction is shrinking, the timelines are speeding up, and yet ice doesn't scream, it doesn't plead, it just moves or disappears, or destabilizes a glacier that held firm for centuries. That's its way of talking, and the message is always the same. Conditions have changed. If the Earth is conscious in any sense, ice might be one of its long-term memory systems, slow to change, but impossible to ignore once it does. Like a dream that gets interrupted too soon, like a balance that's no longer balanced. And if we're listening, we might hear what comes next. Not in prophecy, but in projection, not in panic, but in pattern. Ice shows us what the Earth is trying to restore, and how far we've moved away from it. It tells us with each melt season, and each missing glacier, how the system is adapting to the signals it's receiving. And maybe the most honest thing we can do is answer. It becomes necessary to ask a more inward question, not about Earth or systems or signals, but about us, about what it means to live inside these vast responsive networks, and still struggle to feel them, to understand them, to respond to them. There's a simple reason for that, and it runs deeper than politics or education, or even awareness. It's the problem with being a person. The problem isn't that people don't care, most do. The problem is that we are shaped biologically, neurologically, socially, to pay attention to the wrong things, or at least to things that help to survive in smaller, simpler environments, not global ones, not centuries-long changes, not invisible feedback loops. We evolved to respond to the immediate, the personal, the loud. This makes sense when you think about where we come from. For most of human history, survival depended on reading the behavior of other people, on noticing changes in local weather, on understanding how a landscape shifted from season to season. We lived in communities small enough to track, we hunted animals we could see, we grew food in soil we could touch, and when something went wrong, we usually knew why. Those instincts remain. We're built for short distances, narrow focus, rapid conclusions. Not because we're lazy, but because our minds were optimized for a world where that was enough. But now, the scale of our influence has outgrown our intuition. We're changing systems we can't see, accelerating patterns that unfold over generations, and we're still trying to process all of it, with a brain tuned for campfires and clans. So when the planet sends feedback through rising oceans, retreating ice, vanishing insects, we understand it abstractly, but not viscerally. We can know it's happening, even believe it's urgent, and still struggle to respond in a way that matches the scale of the change. 'Cause the threat isn't a lion in the grass. It's a billion tons of carbon in the sky. There's also the problem of stories. Humans understand through narrative. We look for causes, characters, resolutions, beginnings and endings, heroes and villains. This helps us make sense of events. But ecosystems don't follow plot structure. They're loops, not lines. There's no climax, no final scene, just ongoing balance and imbalance, feedback and flow. So when the Earth responds in ways that are ambiguous, we try to force it into a familiar frame. Is it angry? Is it punishing us? Is it dying? We ask these questions because we're people, and people relate through emotion. But the Earth doesn't feel emotions, not in the way we do, and that makes its responses easy to misread. We also struggle with scale. We see what's in front of us. We prioritize what affects us directly. A flood in our neighborhood feels real, a drought across the world less. So, even if the systems are connected, even if our actions helped cause it. This is sometimes called the empathy gap. It's not cruelty, it's capacity. We're not built to hold the whole world in our heads. And then there's time. The planet moves slowly, our culture moves fast. The life of a tree spans centuries, a career, a few decades. A decision about emissions might matter most 100 years from now, far beyond most people's planning horizon. Our lives are short, our deadlines are urgent, and the Earth doesn't match our schedules. This mismatch creates tension. We want to help, but we want to see results. We want to act, but we want to know our actions matter. And when feedback is delayed or indirect, it's easy to lose motivation, to feel like the system is too big, too slow, or too broken to hear us. Add to this the systems we've built, economies that reward extraction, infrastructures designed for speed, not sustainability, technologies that spread information faster than understanding. It's not that individuals are failing, it's that we were never taught how to be individuals inside a planetary system. This is the hard truth. Being a person in the age of ecological collapse is painful, because we can see what's happening, we can name the damage, but we're not wired to hold all the weight of it at once. And yet we try. We grieve species we've never seen. We study data we'll never use directly. We protest for people we'll never meet. And in doing so, we stretch. We expand what it means to care. We adapt, not biologically, but ethically. This might be the most remarkable thing about humans. We can feel responsibility for things far beyond our immediate circle. We can act on behalf of people not yet born. We can imagine futures we'll never live in. And sometimes that imagination becomes action. But imagination isn't easy, especially when the systems around us are designed for short-term thinking, when the news cycle resets every day, when climate science is buried under distraction, when the Earth's responses are filtered through graphs and forecasts instead of lived experience. This is the real problem with being a person. We're caught between the scale we can feel and the scale we affect. We feel the warmth of a sunny day, but not the shifting jet stream. We see a single storm, but not the global pattern behind it. We experience comfort in the moment and miss the system cost that brought it. And yet, none of this makes us helpless. If anything, it shows why we need new kinds of awareness. Not to replace our instincts, but to extend them. To recognize that caring for a system doesn't require feeling every part of it, but it does require knowing it exists. The Earth doesn't ask us to feel everything. It asks us to listen to feedback, to respond to signals, to remember that being human doesn't mean standing apart. It means being a participant in a system we can only partly see, but still influence. We won't ever be perfect systems thinkers. We'll still miss things, forget things, prioritize the immediate, but we can learn, we can teach, we can organize, and those things over time can shift the pattern. Because being a person is hard, but it also comes with the ability to change what being a person means. The next step is to look outward again, not just at the systems we affect, but the minds we overlook, the minds that aren't human, the ones that don't speak in words or wear expressions we recognize. Because once we start to question what consciousness might look like on a planetary scale, we have to ask what counts as a mind at all, and we begin to see how narrow our default assumptions have been. For a long time, humans believed we were the only conscious species. We were the ones with language, memory, creativity, the ones with art, tools, and stories. But this belief has eroded slowly, steadily, as science has observed more and more behaviors in animals that don't fit the script. A crow can solve multi-step puzzles. An octopus can navigate mazes and escape from sealed containers. Whales have dialects. Parrots invent words. Dolphins recognize themselves in mirrors. Ants use traffic control. Bees communicate the location of flowers through movement. The more we look, the more we find in places we weren't trained to look for them. And the deeper realization is this: intelligence doesn't have one form. It doesn't require a brain like ours or a body like ours. It doesn't even require a central nervous system. It shows up in networks, in responses, in patterns of adaptation. It shows up where systems are able to sense, decide, and act often without needing what we would call thought. Plants, for example, don't have neurons, but they sense light, moisture, temperature, gravity. They move toward what helps them. They avoid what harms them. They signal to each other when under threat. Their roots grow toward nutrients and away from toxins. They even seem to recognize kin-changing growth patterns accordingly. If that's not thinking, it's something parallel, some form of presence distributed across the body. Fungi operate in networks. The mycelium beneath forests spans entire landscapes. It shares nutrients. It redirects resources. It connects trees of different species. It remembers chemical signals. It responds to changes in moisture and pressure. Researchers have recorded electrical pulses moving through fungal networks changing, exposed to stimuli. We don't know what those pulses mean, but the structure looks a lot like a conversation. These examples challenge our mental models. We're used to seeing thought as a function of brains, especially mammalian ones. But what if cognition can emerge in any sufficiently complex responsive system? What if the mind is less a thing and more a process? Some philosophers and scientists have begun to explore this idea through frameworks like embodied cognition and extended mind theory. These suggest that thinking doesn't just happen in the brain, it happens through the body, through the environment, through interaction. When you use a notebook to remember, when you reach for a familiar tool, when your hands guide your thinking, that's cognition extended beyond the skull. It's a small leap from there to say that other systems like forests, reefs, or even weather might also contain the building blocks of cognition, not thoughts as we know them, not feelings, but the ability to integrate information, respond to context, and alter future behavior based on past experience. In that light, the boundary between mind and system begins to blur. The human brain is a system, a forest is a system, a city is a system. Each responds to inputs, each develops structure, each maintains itself, repairs itself, grows. We don't call a city conscious, but it remembers where people go. It adapts to needs. It develops patterns, rhythms, capacities, and no single part contains the whole. It emerges from the interaction of many parts, none of which see the big picture on their own. This is what emergence means. Intelligence or functionality arising from the combination of simpler elements. Neurons alone can't think. Networks of neurons can. Perhaps individual trees don't know anything, but the forest as a network behaves in ways that suggest awareness of change. If that idea feels unsettling, it's worth asking why. Maybe because we've grown used to thinking of humans as the center, or because we're scared of giving up the feeling of uniqueness, or because we don't know how to relate to minds we can't recognize. But if we're going to live on a planet full of responsive systems, ones we depend on and influence, it matters that we understand them as more than background, not just environment, not just resource, systems with memory, communication, flexibility, and maybe in some sense awareness. This doesn't mean assigning consciousness everywhere. It means recognizing that the human form of consciousness is just one version, and not necessarily the most useful one for managing planetary scale systems. A distributed mind might not think in words. It might operate through pulses, feedback, balance. It might not distinguish between self and other. It might not hold goals. It might not be aware of being aware, and yet it could still maintain coherence, still respond to change, still evolve. When you look at Earth from this angle as a network of living, sensing, adapting systems, the question becomes less, is it conscious? And more, how do we relate to its ways of knowing? Because there is knowing in the patterns of migration, in the timing of bloom and pollination, in the shift of ocean currents, in the rise and fall of species. There is knowing in the way coral builds reef, in the way moss colonizes stone, in the way ice holds the memory of air. This isn't romanticism. Its function, its survival encoded in behavior, its life shaping and reshaping itself. And if we can begin to understand that kind of mind, decentralized, non-verbal, pattern-based, it changes how we listen. It changes what we count as evidence, and it might change how we act. Because right now, most of our decisions are built on the assumption that only one kind of mind matters, the human one. But minds are tools, and the planet already has tools. Systems that kept it stable for millions of years before we arrived. Systems we're now pushing beyond their limits. To live well on this planet, we might need more than intelligence. We might need humility, the ability to recognize that we're surrounded by minds we didn't invent, we don't fully understand, and we can't replace if they fail. And maybe that recognition is its own kind of awakening, not for the Earth, but for us. Continuing from the idea that intelligence and awareness may not belong only to the human mind, or even to brains at all, we come to a different kind of question, one that doesn't ask what Earth thinks or how it communicates, but what it is, not chemically, not geologically, not biologically, but fundamentally. If there is something like consciousness across systems, if there is mind distributed in roots, oceans, storms, and ice, then we can ask without irony or metaphor, does Earth have something like a soul? And if it does, what is it made of? The word soul is difficult, loaded with centuries of belief and contradiction. It carries religious weight, philosophical confusion, and emotional complexity. But beneath all that, it often means something simple, the essence of a thing. What animates it? What makes it more than the sum of its parts? In people, we've come to associate the soul with individual identity, the part of us that remains through change, the part that seeks, aches, reflects. It's not something we can measure, but something we feel. And when it's absent, we notice. A place, a gesture, a life without soul feels empty, disconnected. So what happens when you apply that idea to a planet? At first, it might seem absurd. How can something made of rock and ocean and atmosphere have anything like a soul? But maybe the answer is right there in the material. Stone and water aren't symbols. They're systems, and they hold memory, energy, motion. Stone forms slowly under heat and pressure. It carries records of time, layers of sediment, folds of collision, veins of ancient magma. A mountain range is not just a shape, it's a sequence of events. It holds the memory of uplift, erosion, of once being seabed or lava or plain. And water more than anything moves. It evaporates, condenses, falls, freezes, flows. It never disappears. It just changes state, travels, carries information. Water dissolves minerals, transports nutrients, holds heat, reflects sky. It cycles through plants, animals, clouds, soil, glaciers. It connects everything, and everything that lives has relied on it. If there is something like a soul on this planet, it might exist in that tension between permanence and motion, between what holds and what changes. Stone grounds the system, water circulates it. Together they shape all the others. The Earth doesn't have a single center of consciousness. It doesn't reflect in the way we do. But it does carry deep coherence. Storms don't happen in isolation. Forests don't thrive alone. Rivers don't follow random paths. Everything links. Everything adjusts. It is a living continuity, formed from what appears inert. When we talk about the spirit of a place, we're usually pointing to something similar, not a literal ghost, but a feeling of presence. A canyon shaped by wind, a coastline cut by tides, a grove that has stood through centuries. The sense that the land has seen more than we have, that it carries its own kind of awareness even if we can't explain it. And often people feel this without needing to believe anything mystical. A silence in the desert, a heaviness in a cave, the way certain rocks hold heat after the sun sets, the feeling of being watched by a forest that doesn't move. These experiences don't require belief in magic, they require attention. Maybe the idea of a soul isn't about proving something, maybe it's about recognizing something we've forgotten how to name. Because if the soul is what connects, what remembers, what persists through change, then Earth has had one for a long time. We just built cultures that stopped listening to it, systems that turned it into scenery, property, background. But you can't extract a soul without consequences. You can't mine memory dam motion, clear the networks of an ecosystem, and expect everything to remain intact. When we take from the system without feeding it, we interrupt the loop, and the planet in turn begins to answer, not with punishment, with imbalance. When forests are cut, rain falls less. When wetlands vanish, floods increase. When biodiversity collapses, resilience drops. The system becomes more brittle. The loops shrink. The range of possibility narrows. This isn't symbolic, it's measurable, but it feels symbolic because it touches something deeper than cause and effect. It reminds us that we are part of something older, something that doesn't need us, but does include us. A soul made of stone and water wouldn't look like ours. It wouldn't carry memories in language. It wouldn't weigh decisions. But it would still reflect relationship between gravity and motion, between heat and flow, between growth and decay. You see it in rivers carving canyons, in moss reclaiming walls, in the way water wears away the hardest cliffs, in the slow return of green after fire. The soul of the earth is not in a single location. It's in the pattern of return. People used to tell stories that honored this, not to explain away science, but to stay connected to something bigger. The breath of the land, the moods of the sea, the voices in the wind. They were ways of remembering that we don't live on Earth, we live in it. And when we forget that, we risk becoming a force that extracts instead of participates, that accelerates instead of harmonizes, a noise instead of a signal. But that's not inevitable. We can still change the role we play. We can slow down, listen more, reconnect. We can design systems that mimic the loops of nature instead of overriding them. We can build technologies that support restoration, not just production. We can start to treat the Earth not as a machine, but as a system with a kind of presence, not conscious maybe, but not silent and not indifferent. A soul in this sense is not a claim about spirit. It's a recognition of depth, of interconnectedness, of life built on matter, shaped by motion, sustained by balance. And if that's true, then the soul of the Earth isn't something you look for, something you live inside of. We arrive at a question that's both personal and structural. What keeps us looking at all of this with care? What cuts through the numbers, the systems, the science, and still makes us feel something real? The answer might be simpler than we think. It's wonder. And the deeper you go into Earth's systems, the more you realize wonder isn't the opposite of science. It's the reason science exists. We tend to separate the emotional from the analytical, facts over here, feelings over there, but that division never actually held up. Almost every major scientific breakthrough started with awe, not with certainty, but with confusion, with curiosity, with someone noticing something strange and refusing to look away. What's that light in the sky? Why do trees lean toward the sun? How does lightning split the air? Wonder is what happens when the world breaks through your assumptions. It interrupts routine. It makes space for something you didn't expect. And in that moment of pause, the need to understand begins. This matters because we're living in a time when most people already know the facts. The climate is changing. Biodiversity is collapsing. Systems are unraveling. But knowing alone doesn't always lead to action. Data isn't enough. What moves people, what holds their attention, what opens them up to the possibility of change, is often something else. It's the feeling that the world is more complex, more alive, more worth saving than we were told. That feeling is wonder, and the science of Earth is full of it. Start small. A single seed knows which way is down. It orients itself before it grows. That's called gravitropism. A sunflower tracks the arc of the sun, turning throughout the day. Trees communicate through underground fungi. Corals build massive structures from dissolved rock. Hummingbirds can remember the exact location and timing of hundreds of flowers. Bats use sonar to build mental maps of the air. Moss absorbs radiation in abandoned cities. Tardigrades survive in space. None of these facts are new. But when you sit with them, not just as trivia, but as revelations, something shifts. You start to notice how much is happening all the time, just beyond your usual frame of reference. And the more you learn, the bigger that frame gets. Scientists studying climate feedback loops, ice melt, and carbon cycles are also people who get up early to see the sunrise over a glacier, who spend years tagging whales or tracking soil microbes or measuring volcanic gases because they know that inside those measurements is a story worth telling, a system worth understanding, a planet worth protecting. They don't do it because they've given up on wonder. They do it because they haven't. This is important to remember, especially now, because we're surrounded by narratives of collapse. And those narratives, even when true, can lead to fatigue, numbness, a sense that it's already too late. And one of the few things that breaks through that is wonder. Not blind optimism, not distraction, but the reminder that the world is still full of meaning. A spiderweb catching dew, a pattern in a leaf that matches the structure of a galaxy, a cave that breathes, a stone that formed under pressure millions of years before mammals existed. The breath you just took, made possible by algae and trees and air moving across an ocean. Every one of those things is explainable, but that doesn't make them any less astonishing. Science doesn't remove wonder. It adds layers to it. It shows you how connected things really are. How a volcanic eruption on one continent can change crop yields on another. How ancient climate events are recorded in lake sediment. How a whale song can travel hundreds of kilometers through ocean water, bouncing between temperature layers like sonar. And the more you understand those patterns, the more wonder becomes a form of intelligence. Not a soft feeling, a sharp one, a way of seeing that cuts through noise, that pulls your attention to what matters. 'Cause wonder doesn't mean being naive, it means being awake. The challenge is that modern life isn't built for that kind of attention. We move quickly, we scroll past, we filter everything through urgency or entertainment, and in doing so, we shrink the space in which wonder can live. But wonder doesn't need much room. Sometimes just a question, sometimes just a moment. Why does that bird migrate? How does that stone hold its color? What shaped that valley? Why is the tide higher tonight? Every one of those questions opens a thread that leads back to systems, feedback loops, geological time, evolutionary strategy, atmospheric chemistry. Every thread ends in the same realization. This planet is not random, it's not silent, it's not indifferent, it's active, interconnected, and if you're paying attention, always saying something. This doesn't mean we have to be constantly amazed. That's not possible, but it does mean we can build practices that keep the door open. Learning something new every day, paying attention to one small part of the system, spending time outdoors, asking questions even when we don't need answers, choosing on purpose to feel, 'cause that feeling isn't just pleasant, it's essential. When people feel wonder, they tend to protect what caused it. When they lose that connection, they tend to forget why protection matters. The science of wonder, then, is not about magic. It's about meaning. It's about the human need to feel part of something larger, not to dominate it, but to belong to it. And belonging, when it's real, leads to care. This is where science and soul meet, not in opposition, but in alliance. The tools that explain the planet don't reduce its value, they reveal it. And the more we understand the planet, the more we remember that we're inside it, shaped by it, dependent on it, responsible to it. Wonder reminds us that the Earth is not a backdrop, it's a participant, and we are not just users of its systems, we are part of the pattern, continuing from the science of wonder, the engine that drives us to observe, understand, and care. We return finally to something simple, not to the scale of ecosystems or the age of glaciers, or the dreams of tectonic plates, but to this moment, this exact place where you are right now, because everything we've talked about, every loop, every signal, every question of consciousness or balance or soul, it all lands here, not somewhere far away, not in the abstract, but here in the air around you, in the ground below you, in the body you're sitting inside of. Look up wherever you are, the ceiling, the sky, the leaves above your head. Maybe it's quiet, maybe it's moving, maybe it's dark. That space is filled with oxygen and nitrogen and carbon dioxide, the very gases that plants shaped for you over millions of years. The same air that's been inside forests, animals, oceans, factories. Air with memory, air with history. It didn't start here, and it won't end here, but it's with you now. Look around. The materials, the surfaces, the structures, the plastic on your desk, the metal in your phone, the wood in your chair, all mind-grown, shaped by planetary processes, sand turned into glass, oil turned into fiber, trees turned into furniture. Every object carries a story from the crust, from the deep past, from the energy of ancient sunlight. Listen, maybe it's quiet, maybe you hear birds, machines, voices, nothing at all. Silence itself is shaped by your location, by air pressure, temperature, insulation, soundscapes built over time. There are frequencies you can't hear that still fill the space. Electromagnetic waves, molecular motion, subsonic pulses from infrastructure, even vibrations from the planet's crust. Touch something, the floor, the wall, your own hand. You're feeling a surface that exists because atoms repel each other, because matter resists collapse. The texture, the warmth, the pressure, all of it mediated by electromagnetic fields, by bonds between molecules, by physics that operates on every part of Earth at once. Breathe in. That air has traveled. It has moved through rainforests, engines, lungs, factories, deserts. The molecules you just pulled in may have been exhaled by another person hours ago, or a tree, or an animal, or a tide pool, or a volcano. It is ancient and recent at the same time. This is not philosophy. This is structure. You're inside a system made of systems, and even the most ordinary moment is layered with connections. What you call your body is not separate from the planet. It's made from calcium, water, carbon, iron. It was built by DNA, coded over billions of years. You are a geological archive, a walking, thinking expression of Earth chemistry. Your thoughts emerge from the firing of neurons that evolve to navigate light, distance, danger, and care. You are literally a part of the biosphere looking back at itself, and that's not poetic language. That's the most grounded truth we have. So when we talk about the Earth as a conscious system, as a living entity, as a network of feedbacks and memory, we're not talking about something out there. We're talking about where you are right now. Your body is regulating heat, just like the planet. Right now, your senses are responding to stimuli, just like a forest, or a mycelial web, or a river basin. Right now, you are part of the same feedback loops that move air, shift climate, grow food, carry water. You're not outside the system trying to fix it. You are the system trying to rebalance itself. And that's a powerful shift, because it moves the responsibility from something abstract to something embodied. It says the work of repair isn't just about carbon credits or policy changes. It's also about attention, practice, participation, remembering where you are, because where you are matters. Your local weather is part of the jet stream. Your street is part of a watershed. Your daily habits ripple outward through supply chains, energy grids, waste systems, cultural influence. Even your language shapes how others think about nature, connection, value. And when you start to feel that, not just know it, but feel it, you don't need permission to act. You don't need certainty. You don't need to have it all figured out. You just need to start from where you are, because where you are is already full of signals, full of possibility, full of systems that need listening and care. Look out a window, touch the ground, think of the last meal you ate, the last breath you took, the last moment you felt connected to something bigger than yourself. None of those things are separate from the Earth, none of them are accidental, and none of them are too small to matter. You are not apart from this planet. You're not a mistake it made. You are one of the ways it thinks, responds, and continues. So start there from where you are, not as a visitor, not as a savior, but as part of something ongoing, something still capable of balance, something that may already be listening, waiting, adjusting right now.